All right. Next, I'm going to introduce my colleague, Rui Resendes. He is our Director of Partnerships and Business Development. And Rui's going to be taking us through our afternoon program of our startup program. So please, Rui, take it away. Do you want this one?
This one works, right? Want to hear me okay? It works. Perfect. Thanks, Jenny. And thanks, John. What a great way to start our meeting. There's a lot of takeaways. I think the one that I think serves as a natural segue into the startup showcase that we're about to start is that, 80%, did I get that right, John? 80% of things have yet to be invented. So, and there's a lot of places you turn for that invention. And one of the places that I think is, personally, I believe is the most exciting is, what's going on in our startup world. But before I get that, I really want to start off by thanking Procter & Gamble, the folks at Procter & Gamble for sponsoring our startup showcase. So thank you, Pete. We have two people from P&G. We have Todd. I got reading glasses, so it doesn't help if I put them on. It's worse. So Todd and Todd's there, and we have Will, right? Where's Will? Will's there. Okay, so if you don't know Todd or Will, I recommend you get to know them, and what a perfect venue to do so. So, when I reached out to Todd, because, part of the thing I had to do was go get some sponsorship money for the event. So I, of course, reached out to Todd, and, we talked about it for not too long, and he really honed in on, the startup showcase. That's what P&G wants to sponsor. And, it made total sense. My time working with Todd and his team, it's pretty clear that, P&G as a company, from what I've seen as an outsider, is committed to continually improving the safety and the sustainability of the products. And they view these innovations that are coming down the pipeline at various stages, as you'll see from our presenters. They're going to be the solutions to overcoming some of these significant barriers and impediments that P&G and other organizations would have to enhancing the safety and sustainability of their products. So it's, it's a really interesting, organization that I encourage you to reach out to them to learn more, because, not only are they interested in these innovations, they actually want to take a hands-on approach to helping them, right? So helping them connect to and integrate within their supply chain, and ultimately helping them enable their market introduction, which, as a company with diverse markets that serves diverse markets like P&G, it can be quite the enabler indeed. So thank you again, Todd and Will and the P&G team. So I'm going to be very brief here, at least I'm going to try to. So as we start the discussions, actually, I should introduce myself. Let me do that. Hi, I'm Rui, and I'm new to the team. And I know Jenny introduced me, but I really want to ask everyone, if we haven't had the opportunity of meeting, in 3 dimensions, please find me, because I do want to meet you and get to know this community a bit better. But as we, before we get into that, I like to ask everyone just to kind of think of it, like, why are we all here today? Like, why did we travel from parts far and wide to come here today? Is it access to the Nike employee store? It's very nice, and I thank our Nike host for giving the delegates access, but that's not why we're here, right? We're here because, we recognize that we have some pretty significant, health, ecosystem, and sustainability challenges to overcome. We're here because we recognize that the solutions to those challenges lie in innovative new chemistries that, we need to work collaboratively to get them into the marketplace, to become the new chemical norm that underpins manufacturing. And we're here because we know that we need to collaborate. And we don't just need to collaborate with our peer group, we need to collaborate along value chains, and we need to collaborate across industry verticals to make this happen. And this is the community that everyone in this room has built, this community at Change Chemistry, where we take, I hope I didn't check this with Joel, so I hope I don't miss the mark here. I see it as a 3-pronged approach, right, to how we do this. We work with different points of the value chain, different players along that value chain in different industries to try to get some alignment and try to get some collaboration going along that value chain. Aligning market demand signals, very important. And leveraging that knowledge and that insight that we get from doing that to, look towards how can we define and eventually enact new policies, policy frameworks that result in programs that provide real incentives to adopt these emerging technologies. And the third part is, how do we leverage innovation? And that's what brings us to here today, to talk about the innovation that is within the startup realm, which I think is quite exciting. These are the companies that are pushing the boundaries of our technical capabilities. They're challenging the status quo, and they're ultimately paving the way for us to achieve and overcome these sustainability challenges that we have. So I urge everyone here to listen, to learn, to engage, and connect with these entrepreneurs. Help them help us. And it's really important that, they have this forum here, and that, not only do we help them, but they can help us regardless of your position in that value chain. So without further ado, I'd like to invite Cassandra Zentner, who is the VP of Sustainability, of Research and Sustainability at ActNano, and she's going to moderate the first grouping of our startups. And I just have to point out that ActNano, may I call you an alumni of Change Chemistry Startup Network? Oh, so okay. Well, there you go. That's embarrassing thing number one. Okay, awesome. Okay. Well, can we consider you an honorary member now that you've chosen to? Okay. No problem. Anyway, Cassandra, please. Thank you.
So, as it was just mentioned, I am the VP of Technology and Sustainability at ActNano. We are a startup, not part of the cohort previously, but the reason I was asked to moderate today is not only am I a part of a startup now, but I've been a part of startups or research leading to new startups for the last 11 years. So I have been part of 3 different startups as a non-founding employee. So my passion is helping founders bring new innovative technologies and make them real, right? Be the people who help it make a reality. So today, how I'm doing that is by presenting to you all of these new startups who are part of the cohort. And us in this room, our job is to help enable them to make their technology possible. You don't have to be an employee to make that happen. So I'm really excited for there's a lot of very interesting technology that's across different ages. It's from things just founded to ones that have been around for years. And what I encourage you to do is in each of these presentations, think about how you in this room can make them successful and what do we have to do to make that happen. So to kick us off, I'd like to invite Jimmy Chiu up from Loop CO2 to give us our first presentation.
All right. Thank you, Cassandra, and also Rio for the introduction. So I'm very honored to be the first one to kick off our startup demo. And I'm Jimmy Chiu. I'm the CTO and also co-founder of Loop CO2. I'm glad to be here to show you how Loop CO2 can convert carbon dioxide into upcyclable and affordable plastic. So very basic, 2 challenges that we want to face. I think everyone knows this in this room. Carbon emission, that we have been paying so much society costs for our carbon emission issues. The second challenge is the recyclability. So we are now enjoying so much the high performance material, but which are made of like a complex mixture of different materials. So we are throwing away a lot of single-use materials annually, about 100 billion material. So that's basically 2 challenges that we want to address. So how to do it? So Loop CO2, we propose a circular platform coming from carbon dioxide. So look at the cycle on the right-hand side. So we will be making a circular platform from carbon dioxide and biomass raw material to form a cyclic ester monomer, which is shown on the top, and we polymerize the polyester, which look at the center, the Oleo material, which can be formulated to the final product, and later to be recycled back to our monomer material. So by doing so, we offer sustainable raw materials coming from carbon dioxide and biomass. And also we offer the very low temperature chemical recycling that go back to the monomer, which can offer the true circularity. We can repeatedly make the virgin product again. Lastly, our material provide the flexibility and versatility that we can cover from soft material to hard material, and also some chemical diversification. So let's zoom in on the cycle on the right. So first of all, we can combine carbon dioxide with biomass, which the butadiene, which can be bio-derived in scale. We turn into a catalysis process to make our circular monomer, which we call Lumon here. So which is a black and white, that's the parent monomer, which can go through a reversible chemical functionalization to make those monomer on the right that has different color dots representing different properties. Our customers can co-polymerize with different chemistry, just among all those monomers, make different polyesters, then mix and match to formulate into different high performance materials. And then lastly, because all the processes are reversible, So we can go back to the paramonomer again. So back to the cycle. So we all understand this is gonna take a lot of time to develop this. So let's just look at what the paramonomer can do without going through many years to develop this whole platform. So our paramonomer, this is the demonstration formulation that we have done. So we can increase the PLA, the polylactic acid, the ductility by 10 times on from the elongation. In the middle, we have addressed the adhesive formulation that we can increase by the performance by 50% without any tackifier. And lastly, we also make the polyurethane elastomers that has a comparable mechanical strength and also some of the soft features. But more importantly, it has the high chemical recyclability that we have demonstrated in the lab. But we also understand now, the chemical recycling is not just chemistry, it's also the infrastructure. So as a beachhead market, Loop CO2, we want to actually serve the enabler for the PLA. So how to do it? We want to serve as the impact modifier, which has about $300 million in the market size, with about 70% of annual growth in the next 5 years. So why we want to do it? Because the few benefits I list there, but let's just look at a few of them. So first of all, we offer the softest polyesters that can balance the brittleness of PLA. Secondly, our stuff can be bio-based and CO2-based, and also compostable. So we can combine with PLA's compostability to offer a total compostable solution. Additionally, look at the last point, our material can serve as adhesive. So then we can allow the adhesive for PLA. So we can allow the single additive products in this mixture, in this ecosystem. Therefore, we look for no more failed straws or broken 3D printing filaments, but more PLA products. So let's look at different polyesters here. Here, it's not to compare to say we are really the outstanding one, but it's also just to give a different idea about how different materials are covered. So we break down into different three verticals from the raw material input, which is we can be biomass incorporated and plus carbon dioxide. And the middle one is the end of life, where our material can go back to the monomer to go through the recycling in the much milder conditions, as you can see, that's in the presence of a catalyst. And lastly, the hydrophobicity. Our material, by design, introduce more hydrophobicity than other molecules, so we can afford more durability in terms of in certain applications. So here's the team behind the scene. So we have a wide combination from entrepreneur to academia and industrial. Our CEO, A1 Wang, has experience as operation director at Foxconn, the Apple's manufacturer, and also a successful entrepreneur 15 years ago. His business still running independently. In the middle is our CSO, Professor Tunks. He's the key developer of our fundamental technology and very successful in polymer and also catalysis at the University of Minnesota. And myself, so I brought in my experience from DuPont, a specialty polymer, as a technical manager. And also we rely on a strong team of advisors from sustainability, business to engineers. So here's a roadmap to commercialization. Very long, but I'm gonna make it short. So 24 today, we are moving to our 20-liter reactors that give us a sampling capability to our customers. So a few customers already requesting the samples from us. We are preparing for them right now. And then also for the scale up in next year. And 26, from now to 27, where we expect to commercialize our technology, we will be working on those technology transfer to the toll manufacturer. So it's a typical chemical reaction. We don't expect to have large capex by just going with the tollers. And 27, we expect to have the commercialization scale. Then we can start to work on recycling capability and also different monomer pipeline, as I proposed very beginning in that big cycle. And from 29 and onward, then we will be working on the expansion. So what we are looking for today is the forward-thinking partners. So in the past, we have secured $2 million in funding from the government award and also some local ventures, not the local, the state government. So it's non-diluted. And that leads to MVP development, IP, and our kilo scale lab, and also the sampling activity. So now we are looking for the partners that can do the joint development with us to provide the end user feedback and also the offtake agreement in the future. So I'll be here until Thursday. Feel free to reach out to me and we can discuss any kind of details and also talk about what kind of the sampling process. Thank you so much.
We do have time for a couple of questions if there's anything from the attendees.
Thank you. My question is about the catalytic system that you guys use to convert carbon dioxide and butadiene to monomers. If you can talk a little bit about it.
Yeah. So that's a good question. We are using precious metal catalyst, which we understand that will be highly related to the cost and also carbon emission. So we definitely have some strategy to focus on that in order to keep it as an asset instead of consumables. So thank you.
Do you guys still keep developing and improving the catalytic system, or it's already sound and solid to scale it up?
Yeah, that's definitely our key milestone, because to be honest with you, I just want to be honest to the audience here. The catalyst cost definitely is a huge contributor to our technology. So the next generation catalyst is the key to lower the cost. Yeah.
Thank you.
Yeah, thank you.
Thank you.
Please be sure to use the mics when you speak, guys.
Yeah, it's hard to hear.
Thank you. I like the concept. I think the future is replacing carbon-carbon backbones with carbon-oxygen polyester type. So polyethylene, polypropylene, especially in non-durable packaging, will be polyesters. But I would caution you that PLA has been made flexible. There are all the elements of adding blended polyesters to it to give a product. It would be more valuable for you to develop end application product specifics. In other words, I'm going to make a flexible film and this is my cost, this is my performance, versus providing, a polyester-based material to be added into, say, PLA. So just a suggestion for you to think. I'm happy to talk to you. PLA was developed at Michigan State 20 years ago, and there are 4 major industries, companies manufacturing PLA today, right? NatureWorks, Total Energies, Corbion, and more recently in India, there's a PLA manufacturer, and in the Middle East, of all places, they're going to build a PLA plant. So certainly, these kinds of products would be very valuable, and I ask that you reach out to them as well.
Thank you so much. Yeah, we are getting samples. The samples we're doing is from NatureWorks, since we are a spin-off on University of Minnesota. So we have that Minnesota alumni networking.
Hi,
Jimmy.
Excellent. Thank you very much. If you have any other follow-up questions, of course, please find Jimmy as the day goes on. Thank you very much for your presentation on Loop CO2.
Thank you, everyone.
All right, excellent. So we're going to keep this rolling through. We have a lot of exciting startups to talk about today. So next, I'm going to invite up Stephen Mayfield and Nick Sandland from Soleic by AI Genesis.
Excellent. We're tag teaming you guys today. So my name is Steve Mayfield. I am the founder and chief technology officer of Algenesis Labs. And what we make is a biodegradable polyurethane. I won't go into how many, we started, aiming for the shoes. Now we can make a lot of different things with it. I won't give you guys a number except to say it's alarming how much plastic there is on the planet and how much of the plastic products that we use turn into microplastics. And I'm sure all of you have seen the papers that have come out over the last year showing that these things are in the water we drink. They're now in our arteries. And I saw a report a month ago that said 0.5% of human brains are now microplastic. Some of us, I think, are a little higher content than that. Some maybe a little lower, I don't know. But I think this is something we really have to address. And we thought about this when we started the company. We're a spin out from UC San Diego, and specifically we aim to make plant-based polymers that would biodegrade at the end of their life. Originally, we were thinking, oh, we'll do this because we've been growing plants and algae on this planet for over 3 billion years. They've never caused problems. When I was born, we did not have plastics. Not in this country, not anywhere. In fact, even growing up, we never had a plastic product till I was in high school, right? And then my father, so happy when he bought our first plastic slide for us. And of course, my brothers and I trashed it instantly. So this is only in the last 50 years. So the idea behind ours was, can we make a high performance polymer that meets specification for all of the running and jumping and sliding and the rest of the things we need to do, but could be biodegradable at the end of its life? We specifically targeted polyurethanes because if you make a polyester polyurethane, inherently it can be biodegradable. So that is what we did. Right, as I said, we're a spin out of UC San Diego. I saw our little name there on the slide showing that we're part of Change Chemistry and part of Beyond Benign. I didn't know that. I'm very happy to know that now, right? And so what did we do? We started out, the basic idea was plants are very good at making hydrocarbons. Those might be fatty acids, those might be isoprenoids, those might be long chain acids or alcohols. We could take those and stitch those together to make a polyester backbone that we could use to make a polyurethane. So we've done this. We made shoes. Both Nick and I have them on today. We've made about 15,000 pairs of these. We've worn them now for 3 years. They are just as durable as the shoes made by the company who we are visiting today. The only difference being that ours will biodegrade at the end of the life. And as I said, we think the important part of that is not so much that you're going to compost these things, you could, but we think the important aspect of that is that the microplastics that you abrade off them while you're walking or wearing them or doing whatever do not become microplastics that end up back in the water and ultimately in your brain, okay? So what do we have? We have high performance plant-based polyurethanes. They have about, right now, our present ones, we make the polyol portion and we buy petroleum-based isocyanates. People always ask me, how can you be biodegradable if 30% of your thing is from petroleum? Because all organisms care about is what is the bond. The bond between an isocyanate and an alcohol is a urethane. That's why they are polyurethanes. Urethane bonds are very common in nature. Organisms know how to degrade them. Now, what's in between those two urethane bonds can determine whether there's toxicity, but both MDI and TDI and the rest of the aliphatic isocyanates we use are not. We test that and we publish that, okay? So we are biodegradable. We have third-party validation on that, no ecotoxicity, and these things work really well, right? So I am now going to turn this over to Nick because we actually have these products on the market. We sell monomers. We sell either what's called an AB system, that's how you make foams out of it, or we also have something called a thermoplastic polyurethane, TPUs. Those can be used for coating fabrics or doing injection molding. And we actually have both of these things on the market now. And our chief business officer will tell you how you can get them from us or collaborate with us to find out if our TPUs and AB systems can work to make your products.
Thanks, Steve. So yeah, Steve's done the sciencey bit. I'm going to do the commercial bit. So, as Steve says, we've been around for a few years. I was brought in about 6 months ago to sort of help commercialize the products. And I've been working furiously over those last few months to try and sort of put all the right things in place to turn us into a sort of a functional business that we can supply major brands in the industry. So we're building out that supply chain so we can do polyurethane systems, we can do TPUs, and we've got toll manufacturers in place in various locations around the world, so we can produce, hopefully in the next year or so, we'll be able to produce locally to those manufacturing markets as well. We are in that industrial scale up. We've just completed multi-ton runs of the polyols and the TPUs. As a result of that, we have products in the warehouse. They're available for sale today. And as Steve said, we created the Blueview shoe brand as a sort of proof of concept to show that you can produce high performance, well-designed materials that go into these products.
again, in the footwear industry, this is one of our main focuses, and we can help you with that. We've designed our own shoes. We've tripped and stumbled and made the mistakes that a lot of people make. So we can help people not just by providing the material. We can provide some guidance on some of the ancillary processes, some of the other materials that get used in the footwear construction as well. Again, in terms of I'm not sure if there's anybody from Nike in the audience, but we've got, Soleic is an option today. We are working with the factories around the world that produce for the major footwear brands. We're working with the brands, but we also want our product to work in the factory in high volume, day in, day out, week in, week out. There's a lot of drive coming from the markets today. There is a chance to improve market share with sustainable footwear. We do see a lot of brands have had their reputations damaged. Again, there's a chance where people can regain that brand value. And this is a revolutionary innovation. We genuinely believe, it can drop into existing factories, but it does provide something that nobody else provides today. And we do see line of sight to cost parity as well. Again, today we're at small scale. It's a challenge to get to that exact cost parity, but we do see line of sight within the next 3 to 5 years. And so what do we need to scale the business successfully? We need those major brands who control large percentages of the market to take action. There's a lot of people, everybody wants to talk. What we've got to do is translate that talk into action. We have to get better education on biopolymers and biodegradation. There's a lot of debate around, well, what is this, what is that? And that just burns time. So better education. Governments and NGOs, definitely, they need to put that legislative change in to level the playing field. There are taxes and duties that are coming in around the world around petrochemical materials, low carbon footprint, biopolymers that will help level out that playing field as well. And we need that infrastructure to handle things at the end of life as well. A lot of people don't want to use biodegradable materials because they're scared of potential end of life issues. So understanding how we treat those things at the end of life is extremely important. But as Steve said earlier, the connection between something that is biodegradable and the fact that that does not create persistent microplastics, particularly in the footwear industry, is extremely valuable. And again, we're working on our own isocyanate developments. This is a very, very important thing. We've spent several years working on that. We've just got our pilot facility in San Diego operational. We're at that kilo scale today. We are designing an industrial scale plant with support of the US government. And so this is something that will be coming soon, and hopefully we'll get an opportunity to talk to you about it in the next few months. So thank you very much. If there's any questions, we'll do our best to answer them. Yeah.
So are there any questions? Are there any questions from the crowd? Okay, please wait for the microphone and state your name whenever you ask your question.
Yeah. My name is Yuri and I'm from Kenview. It's formerly J&J Consumer. What is the feedstock for polyol that you guys make?
We have, originally the company was built around algae as the feedstock, but it became pretty apparent that that was not ready for large scale business. So we've adapted the technology. We can use a number of different plant sources, but hemp, castor, they're probably the most commercially viable today.
Yeah, thank you.
I will take one more question.
Hi, just a question about the biodegradable to prevent the persistent microparticles. As a concept that makes sense, is there a way that you assess that?
Absolutely,
Either,
yes.
by...
Steve can talk in intimate detail. In fact, we've actually had a scientific paper published by Nature on that very topic.
Yeah, so it's not that hard to actually measure whether something is biodegradable.
Do you want to? Yeah.
It's actually not that hard to know whether something is really biodegrading or not. Sadly, the industry has spent a fair amount of energy greenwashing and trying to confuse people about these things, and there are just a bunch of people who will lie. We don't. We actually have scientists who work for us. I've got a PhD, and we publish these papers and make it open to the public. Happy to send you a copy. We published this in Nature back in March. We did this by grinding up one of our shoes and one of the phone cases made from our material, putting it in compost, and then watching both the disappearance of the particles and the increase in CO2 over time to demonstrate that we could go down to 0% residual microplastics. And the paper is available.
Thank you. Would love to see that paper.
Thanks.
All right. Thank you very much to Steve and Nick.
Thank you.
So next up, I would like to invite Chris Shugart from Ambient Fuels.
Good afternoon, everybody. Thanks to Change Chemistry for putting this together. I know this is my first time attending one of these events and already enjoying the time spent with everybody here and looking forward to getting to know a lot of you over the next couple of days. So my name is Chris Shugart. I'm the Senior Vice President of Development for Ambient Fuels. By the way, the date, okay, I'm hoping this is the right slide deck. I spent my whole career building things. Started out in gas turbine power plants, and then moved into clean energy in about 2006 and spent better part of my career in wind energy, building wind energy facilities, which have been a big part of decarbonizing the world so far. Let's go to the next slide. Oh, that's me, sorry. So, you know, as I spent a lot of time in wind, had become a very mature business, I was really looking forward to what's next for decarbonization, which has been the focus of my career and my colleagues. And we said, you know, wind and solar are going to do a lot of the decarbonization in the world, but there's about a third of the CO2 emissions that really need a molecule solution where there's not an effective electrification pathway. So we looked at technologies and said, as we'll talk about a little bit here in this talk, hydrogen was the solution that we thought was going to be a big part of the remaining tougher decarbonization challenges out there. So we built this company, started about 3 years ago. We are actually not a technology developer. The technology that we use has been around for a long time. It's been used on spacecraft and submarines for a long time. But it really needed a lot of deployment. And so the technology is there. About 6 months after we formed the company, we had the good fortune of the Inflation Reduction Act passing, which had the most lucrative clean hydrogen production incentives in the world. So we had that. So what we really needed was teams that got to know this technology real well and could aid in the deployment of it. So we put together all the pieces that you see on the right-hand side of this slide. These are all so we are not a technology developer, as I said. We take commercially available technology, but we deploy it. So it's all the things on the right-hand side. These projects are complex, take a lot of time and money and capital to put together. So how do you put all those pieces together, working with end customers, working with suppliers, siting, permitting, bringing capital into the project or into the industry? These bullets here give you a pretty good idea of the kinds of industries that we serve. A lot of chemicals production, transportation, heavy industry. These are all things that have those challenges I talk about that are difficult to resolve just with electrification. You know, I'll go quickly on this. I'm on the startup panel, but we actually have capital behind us. This is an exciting space, and there's a lot of capital that's interested in deploying these clean technologies. So we are a developer that's agnostic about the exact technology that we're deploying, and we bring in Generate Capital, our backer, with capital ready to build projects for customers. And I'm realizing that I sent an old slide deck, it appears. So I'm going to go off script for a minute here. You know, actually, let me take one more thing here. Yeah, okay. I have the wrong slide deck here, so I'm going to go off script for a minute. Hydrogen, if you're familiar with it, first of all, the technology we're using is electrolysis, so clean electricity and water making hydrogen and oxygen. And so it's once you've made that clean hydrogen molecule with no carbon content, there's lots of different directions you can go with it. It can be a feedstock into chemical production, a feedstock into clean fuels for shipping, for aviation. It can be a source of heat. And so it's a Swiss Army knife, if you will. When I think about this audience and in chemistry, I think about a couple of things. Certainly feedstock, working with HDPE manufacturers, for example, who are using hydrogen now in their reactions or hydrogenation reactions, going downstream, making chemicals like ammonia and methanol, and then all the derivatives you can make from those. These are all pathways where all you're using is wind and solar electricity, clean water to make those products. And then in some cases, those cases I described, combining it with CO2. So we're working with a lot of partners around the industry, the ethanol industry, for example, which has readily capturable carbon dioxide and the ability to combine that with hydrogen to make all kinds of fuels. Within hydrogen today, if you're familiar, almost all the hydrogen today is made from a process called steam methane reforming, which is basically just taking a methane molecule, cracking it, taking that valuable hydrogen to use, but then emitting all that CO2. So it's one of the bigger sources of CO2 from chemicals and heavy industry in the world. A very proven and low cost approach, but a very carbon intensive one. So we take a fundamentally different approach where it is electrolysis of clean water. There is no CO2 emissions. It is just clean hydrogen. Trying to remember what my slides were. This is embarrassing that I set the wrong slide deck. Sorry, everybody. So maybe I'll go to questions in a moment here, but what we're most interested in working with a group like the group here is we quite often go to, it's funny, I often spend my time with folks like LyondellBasell and Dow and folks like that, who I interestingly notice are not in the room for the most part. There's some of their, a couple producers are. A lot of them tell us, hey, we're just beginning to see a pull from downstream, an interest in carbon footprint and decarbonization. But that's what I love about this organization, putting the supply chain together, creating the pull, because there are opportunities for this that actually reduce cost out of the gate. And there are others where it needs some price on carbon to make it effective, but can be pretty low costs of carbon to compete. So interested to meet a lot of you over the next couple of days if you're thinking about chemical production processes that do use hydrogen as a feedstock. This is a big mover on the needle on the carbon scoring of that. I know we have a lot of retailers in the room. I know moving the products, so aviation, shipping, trucking, those are all industries where hydrogen and its derivatives can play a part. So looking forward to meeting some of you. I'll find my correct slide deck later so that it can be available for everyone. I had some pretty cool pictures I was hoping to show you. Anyway, I'll pause there. I'm here for the rest of the event. Happy to talk to folks one-on-one about the solutions and the pathways. So any questions? Thank you.
Do we have any questions from the crowd? Well, I can start us off.
Sure.
So in some other conversations I've heard, we're kind of at this inflection or critical period for hydrogen as a fuel source. Can you speak a little bit to how you're seeing that kind of in the marketplace and what you guys are doing to really make that inflection go up?
Great question, because certainly when the Inflation Reduction Act came out, there was a lot of hype around this and a lot of news around it. I would say a couple of things. There are low-hanging fruits where we're seeing things get done. We've seen, we didn't see as many projects going into construction this year as I would have guessed. We saw quite a few in Europe, which has been a little bit of us ahead of us on this. But a healthy pipeline of projects. I think what we're seeing the most interest first is, number one, those use cases where it can actually save money. So I mentioned working with an HDPE producer. I'm working with one where they actually, the hydrogen's produced far away, it's liquefied, it's put on a truck, it's driven cross country, and then revaporized. That's a pretty expensive process. That's a kind of a rare example where we can actually come in, save cost and save CO2, and that's an easy business model. The other place that's gotten a lot of interest that I think my friends from 12 are on the next panel later today. Europe has a fair bit of mandates for shipping fuel, aviation fuel, things like that. So a lot of interest in what we call e-fuels, combining hydrogen and CO2 to create downstream fuels, where there is both a European compliance market, but there's a kind of nascent but growing U.S. Voluntary market as well. And then a lot of other use cases in between. And there is, I say electrolyzers are a lot like solar panels and batteries. The costs are 100% certain to come way, way down in cost as the industry scales. So that's what I'd say. Last bit I'll say to your question, if you're following the news, the final, that Inflation Reduction Act that passed 2 years ago, we still don't have the final rules yet, but it's expected in December of this year. And I think that'll help out a lot to give certainty to the incentives, which are an important part of the industry.
Great. Thank you very much, Chris.
All right, thank you.
All right, next up, I would like to invite Mike Uelling from Blueprint Climate.
Thank you. First, I want to apologize. I'm a last-minute stand-in for my co-founder, Ben West, who's not nearly, and I'm not nearly as handsome or intelligent as Ben, so I'm going to try to represent this as well as I possibly can. And we're a little bit different than some of the other presentations that you guys are going to see today. I think this group understands the challenges we have. The number of billion-dollar environmental events related to climate are escalating at an exponential rate. Interestingly, Oregon along the way is suffering economically from not participating in the solutions for those climate events. And we have kind of a bigger vision, right? We see Oregon regaining its mojo in climate innovation. See it boldly stepping forward, advancing solutions that are both economically and climate viable, and attracting the world's best and brightest to come along on the journey with us. When I look around the room today, this is a great example of that, right? And so what are we talking about doing? We believe that we can build a supercluster focused on climate innovation in Oregon alongside of a venture builder backed by an AI-driven technology solution. So those of you who may not be familiar, a supercluster or a cluster is essentially an economic development engine where you get government, researchers, innovators, capital markets, industry to come together in a coordinated way. It's a way different thing than what Silicon Valley does, which is an incredibly organic solution. This is a coordinated effort, right? And a venture builder is an emerging investment vehicle that is still pretty nascent in its execution, but it's a way more involved process. It's essentially a startup machine that comes alongside with expertise, processes, phase gating to either advance technology more quickly or to kill ideas that are just not going to be market viable as early as we possibly can. And our insight really is that at this moment in history, we have a once in a lifetime opportunity to create economic activity while saving the planet. And there's an interesting characteristic in a lot of these solutions where traditionally you would see innovators emerging in urban settings and most of the benefit landing in an urban environment. All of these climate solutions, for the most part, have a rural development component that goes with them. And so what that allows you to do is bring everybody along for the economic ride while you're fixing the problem. And what is the technology? And this is something that has been used in pharmaceuticals for a long time, but to find alternative uses for technology. But what we're talking about is building out an ecosystem knowledge map, understanding actors, being able to do deep analyses of impact, whether it's policy, alternative utilization, alternative technology deployment. There's a lot of ways that you can use these kind of technologies. It's dynamic and it's in real time. There's a heavy human in the middle component of this work because we still can't make those disassociative leaps, and ecosystem mapping is something that you have to go pretty deep when you're building it out to make it effective. But we're seeing results from it already. And there's kind of an art to this where you need to sort of capture all the complexity, but make it simple enough that it's utilizable. And I think for us, we believe there's an opportunity because as we engage with other groups that are trying to accelerate innovation in the space, there's a real lack of leadership. And so what they're saying to us as we're proposing solutions and building out the ecosystem is help us. And that has been honestly the most fun in the process. And I'm going to skip up. Let me do this. This is the remarkable thing, because the traction we have made already in less than a year has been incredible. So in Oregon alone, city, state, federal engagement, we have partners in national labs. The Department of Energy already is jumping on board to partner with us in this journey. And we even have international interest now. And that is a remarkable thing. The way we got into this panel is our very first company is actually Aerocarbon, which is in the carbon conversion technology, working to create base level chemical inputs using carbon feedstock. So John talked a lot about how do we convert what we've got into feedstock. That's what Aerocarbon is all about. I think to me, the most remarkable piece of this is in this space, leadership matters. Okay. And John, I love what you were saying earlier about how we step into the space and help the decisions be made more efficiently. We just raised a flag, guys. I mean, we just went out there and raised a flag and said, we're going to lead in the space. We're going to try to galvanize people around the solution. In less than 6 months, we've already raised over $10 million for climate companies based in the Pacific Northwest. We've already engaged over 30 organizations in the space, spanning from British Columbia all the way down to Northern California. Just by moving, we've created impact. And I think that's the thing that we're most excited about. And so we're a little bit different. We're trying to enable everybody in the room to succeed along the way, and collect a posse of amazing leaders, innovators, researchers to help accomplish the goal. Any questions?
Any questions from the audience? All right, so I'll hit you with one. You say you're a little bit different. How did this actually come about? Like in terms of the first origin of something and this idea that is a different approach than what maybe other people have seen before?
Yeah, that's a great question. Thank you. We started off with Aerocarbon, actually. It's a NYSERDA funded research program. And what happened was, as we were assembling the leadership team for Aerocarbon, what we realized is that team had the ability to make a bigger impact. And frankly, we all said, if all we did was do this, could we disrupt the petrochemical industry? Yeah, we probably could, maybe. I mean, it's early, right, John? It's innovation, so we don't know how it's going to play. But we realized is the team we had assembled could help everybody else win. And that was when we sort of broadened the scale and scope of what we were trying to undertake and say, well, let's use our superpowers for good as a collective. And it's gone from there. I mean, I think that's been the remarkable part of the journey is how many people have raised their hand and said, I just want to go with you. I don't even know what I'm going to be doing with you, but let me come with you. And they're bringing more allies to the table and more companies. And it's been remarkable.
Thank you. We have time for another question if there's anything from the audience.
Great. Thank you. Oh.
I just wanted to hone in on your name and ask you what's next. Surely you're not staying in the Pacific Northwest, right?
Yeah, actually, we are now being pulled in other directions already. We've been pulled north. PNNL is really interested in doing something meaningful. Their words were, we've been waiting to do something meaningful with Oregon for 3 decades, and now you guys have raised your hand, so let's go play. So Washington is already pulling us. Had an interesting conversation 2 weeks ago with the government of Taiwan. They're fired up because they invest a tremendous amount in a semi-coordinated innovation pathway, but they want access to the US expertise. The risk profiles of our capital markets are way different, and the market, of course. But we're getting pulled in some interesting directions, and we know that at the end of the day, we're going to end up engaging in a more broad way. the Colorado, Wyoming supercluster that's focused on resiliency. They want help. The London Climate Innovation Supercluster, they're interested in partnering. So yeah, we're getting pulled in a lot of different directions at this point. But from my perspective, that's a good problem to have. Yeah.
All right, thank you very much, Mike.
Thanks.
All right, next up, I'd like to invite Amy Heintz from Battelle.
Guys, it's really nice to be here. So I am from Battelle, and we are not a startup company. We've been around 100 years, and in particular, the place where we sit is our mission is to help industry by taking things that are going on in academia, in early stage science, and translating that, developing new technology, de-risking it, really doing the entrepreneurial work to both invent and help it to be successful. And I lead a part of our organization that really is that entrepreneurial arm, where we have groups of people who are doing bottoms-up idea generation, and we seed those inventions. They're not targeted towards anything in particular. It's just what they want to work on. But then we do other like bigger investments, $1 million, $2 million for a few years, where we see a need to change the conversation. We see that industry has a need, but there's not the inventions needed to address that need. And we do that in areas in particular that leverage innovation in chemistry, biology, and material science. And so one of the things that we're very concerned about is plastics. Now, I'm a polymer scientist. I first became interested in polymer science because of all that you can do by changing the chemistry of the polymer, how it organizes in the process to create all different kinds of products. And certainly with textiles, you know, that contributes a lot to a lot of the things we appreciate about textiles, the feel, the washability, the waterproof, you know, you're out there hiking, all the things that you like to get from a textile come from this power of polymer science. And yet there's no good end of life solution. We love what we're seeing from communities who are working to add circularity in by developing collection programs and developing new uses for textiles, making curtains from shirts. That's wonderful. And yet, when we look at what we're talking about here, we've got 100 billion new garments are made each year, 92 million tons of textile waste, and really 87% of that ending up in landfills. So recycling seems like a perfect solution. And at the same time, recycling is very challenging for this particular area. Recycling works great when you can take the energy that was already put into that substance and use less energy to make something new. Perfect example is aluminum. Aluminum recycling works. The economics for that work. It's very energy intensive to take bauxite, to take a can and remelt it and remake a new can. Great. So the problem with plastics, and in particular for textiles, is that you've got these intimately mixed things that can't be deconvoluted. It's not as simple as being able to mechanically disentangle them because they're chemically or molecularly intertwined. So what we're trying to think about is, can we address the challenge that the value equation doesn't work? Can we look at each of these pieces, whether it's the collection and sorting, the deconstructing and purifying, and then making something new? Can we take a look at that and solve a problem in any of those areas to help make the economics work? So we want to introduce Green Loop. So Green Loop is, we're aiming to circularize mixed waste recycling. What we're taking is very challenging mixed waste feedstocks that can't be addressed other ways. We're targeting textiles and also packaging, taking those things, chemically deconstructing them, and using biological funneling, we call it, to upgrade that into things that can then be separated to create then a set of biopolymers. So in summary, we're taking mixed textiles that are made from petroleum products or biodegradable sources, and then we upcycle those into things that are biodegradable by design. So it's a really new way of doing things. So let me tell you a little bit about what it involves. When I saw where this room was, I was like, they're not going to be able to see this picture. So here's what this picture shows. What we start with is a deconstruction step where What we've looked at to date is mixtures of things like nylon, nylon 6, nylon 6,6, polyurethane, polyester, cotton, those kinds of blends. Take those and we deconstruct them chemically. What does that mean? Well, it means we heat them up. We're using a hydrothermal process where we can take those things and break them down. And our goal is to break them down usually into monomer, but really we create a water-soluble broth that contains also still the dyes and everything else. And we take that broth and we feed it to a biology that likes everything. This biological entity has been directed evolution to eat terephthalic acid, to eat adipic acid, to eat ethylene glycol. And if we get it right, we can have all of those things eaten and then upcycled into polyhydroxybutyrate. Now, why do we choose polyhydroxybutyrate? Well, in fact, this polymer is already made this way in industry, but instead of textile feedstock, it uses glucose. So we think it's a nice system to be able to try and address this. So some of the advantages of our system. One cool thing is we can completely handle these dyes. We can take a pair of jeans or something that's a black t-shirt, and without any kind of solvent exchange between those steps, we can completely go from deconstruction to PHB. But also very important is we can deal with things like PFAS or brominated compounds. Now, I want to be very careful in the language that we use here. We have early results that suggest that we can take things that contain PFAS and brominated compounds and deconstruct those and safely handle those. We need a lot more study to prove that, but it looks like a very promising approach for being able to handle both the recycling problem and the environmental issues associated with those materials. We think it's great that it creates a biopolymer that we can then put back into the same recycling loop or decompose other ways, and then it doesn't require any kind of sterile fermentation process. So we use LCA and TEA to help guide our design. And I likewise want to be very careful in how I talk about this because any good TEA really depends very much on the use cases. But just to compare a few case studies, one would be to look at our system versus reselling it versus a landfill disposal versus incinerating for energy. And what we see is, of course, no surprise, reselling has the best benefit. The challenge with resell is really just this transportation aspect. So the fact that you have to move things around has a cost associated with that. The cost also means jobs, so it's not completely bad from an economic standpoint that way. But there's some advantages to being able to have a Battelle green loop kind of solution, used in parallel for that. So we see that our system has a very good net benefit compared to other approaches. So where are we? Well, where we are, we have demonstrated this technology to technical readiness level 4. What does that mean? It means we've shown things at a system level. We can do 50-liter batches for the funneling, for the biological funneling, and about 1 kilogram of deconstruction on the chemistry side. So that's kind of the scale we are. We've shown that we can do a variety of polymers. We can put them all into the same flask. We have the TEA and LCA to show that if this scales the way we predict it can, that we can be cost competitive with a PHB. Now, PHB is, not the price of a PET. It is more expensive, so there's still that. So really where we're headed next is first getting that market feedback, and really important is getting some specific partnerships so that we can develop the right kind of use cases, because that's what it's going to take to scale the interfaces appropriately. So I would love to have chats with you guys about the kinds of things that you need and see if we can maybe sample some product to you or use your waste feedstocks to create some new material. So with that, I'd be happy to answer any questions.
Okay, we have a question in the back.
Thank you. PHB and PHBV has been in the market for the last 40 years, all the way from ICI. They have still not made it into the commercial marketplace, competing with other polymers. Why do you think another PHB is going to make it into the marketplace? And what is it going to make it different than all the companies which are today marketing PHAs?
Yep. So we like PHB because it's in the market. Because I think it's in some ways it's challenging. Yes, it hasn't taken off the way PLA has, but there is a market for it. And I think the problem with PHB is it's too expensive. So I mentioned, we're at price parity with PHB. It's $2.50 a kilogram. That's PET is $1.50. So we've got to bring the price down. And to me, when the price comes down, that will open up a lot of applications. I also like PHAs in general because they have a lot of what I like about polyolefins, that you can change side chains, you can change formulation. Again, the cost hasn't been low enough to allow that balance. But to me, I think that's the key, getting that cost down. Just my opinion.
All right, thank you very much, Amy. Apologies, we have a lot of startups to get through. I know there's some more questions in the crowd, and please find Amy after these in the networking break. All right, excellent. So next up, I'd like to invite Jan Weernink from GFBiochemicals Re-Chemistry.
Yeah, this is right. The picture should be upside down. Hi, I'm Jan Weernink, CEO of GFBiochemicals. We're rebranding the company to call Re-Chemistry. To John's point earlier, we have to do things differently and we have to be creative. So rethinking chemistry, redoing chemistry. So we figure out we're going to be Re-Chemistry. We're going to redesign ourselves. I'm going to talk to you about three things: the company, to introduce ourselves. I'm talking about the impact, and I'll talk about the application spaces. The company was founded in about 2013 by a former soccer player. And when you talk about people that have passion, this individual was playing for Arsenal and AC Milan. And he decided to get into the sustainability because he felt a passion for it, which I think up until today, it's amazing to see that energy. And he's put his own money into it, so he's made this his own company, and I think that's very admirable. And it's still here. So we're not a scale-up, we're a scale-up. Sorry, we're not a startup, we're a scale-up these days. We've actually gone from 2013, first ideas, working with universities, all the way into being commercial. We're actually selling product. We have manufacturing capabilities. We're actually getting ready to build a plant, which is a tremendous feat. So we had a number of partnerships and acquisitions in the course, but we're still here. A lot of startups, don't make it this far. I think it's an admirable thing that we've gotten to this point. So I think I want to show you the map. So we're also available in North America. So we have a facility here in the US. We're mainly a European company. So we're based out of south of France, which is for me a very nice thing because I get to travel from Belgium to south of France on a regular basis. But that's also where we are going to build our plant. We're looking at a facility in the port of Marseille. We actually have current tolling capabilities in Asia. So we're actually well on our way for commercialization. If you think about what our technology is, we take bio feedstock, so basically agricultural waste. So we're not competing with the food security discussion. So we take the agricultural feedstock, turn it into levulinic acid, which then in situ taken further into the esters and ketols as solvents or emollients or other types of products. So it's a process that is quite complicated. And I think, John, you probably recognize this. This was developed by the DOE in 2001, 2002. There was first reports, levulinic acid being the first, or one of the 12, was it 12 or 25 platform chemicals. And in 2011, they redid a study again, and it was levulinic acid was still part of that journey. So levulinic acid as a chemical, as a molecular species, is a very interesting one because it can form many, many different reactions and can form a basis of a lot of different types of end products. So the company's developed the processes over the last, I would say 10, 12 years, to solidify the technology. So it no longer is a 1 liter or small scale production capability. It's actually commercially available in large quantities, and to the point that we're actually ready to build the plant. So what is our impact? So if you think about it, we're taking agricultural waste material, corn or sugarcane materials. We do a catalytic conversion and we turn it into an ester or a ketal, which is then serving many different industries. You think about paints and coatings, home care, I&I applications, agrochemicals, personal care, and there's even a number of other applications possible. You think about some of the ketals that we have that can serve as a bio-based plasticizer, for example. So there's a lot of end-use applications for the products that we designed. The nice thing is, because it's the way levulinic acid is transformed, once you create the esters typically hydrolyze, so it's a strength and a weakness at the same time, but therefore they become biodegradable. And ours are fully biodegradable as well. So you have solvents, for example, that can be completely turning back into agricultural, I wouldn't say waste, but they're actually completely biodegradable. We've done some LCA work, and you can compare an average standard solvent in the black box over there. Let's say it's about 5 or so. Our products on a normal LCA are showing a significant improvement in CO2 footprint reduction. If you take the +1, -1 method, we're actually negative, because we're coming from carbon from the agricultural waste. You actually have to take into account the CO2 that's sequestered into the plants. And that is not done in a normal LCA. So this is actually not even a fair, I would say, a full picture, because you're not taking account of that sequestered CO2. Once you do that, you get to negative numbers. And I think that's an extremely important feature. And we're starting to do redo the LCA work and redo the test methods for it. Also, if you think about the biogenic carbon levels, they're nearly 100%. The reason why a couple of the grades are not 100% biogenic carbon is because some of the ingredients like butanol is available, but it's not very widely available from a bio-based source. But even if butanol or some of the other ingredients become bio-based, our products are going to be 100% bio-based. So the applications, if you think about it, this may be a bit of a technical, but if you look at Hansen solubility parameters, you start looking at how good these products actually are. You can compare with alcohols, glycol ethers, you look at oxygenated solvents, you look at aromatics. All of them have their own characteristics and certain performance profiles. Our products are a little bit different, but they're very strong solvents. They're so strong that in our manufacturing facility, we had to redesign all our seals and bonds because they were eating away by the solvents that are coming out. The chemical structures offer multifunctional properties because there's a double ketone bond on there, so it has antimicrobial functionality as well. And there's some patents around it that prove that. They're very ecotox friendly, so biodegradability is actually extremely good. And then they have a very low carbon footprint. And as I mentioned, if we do a +1, -1 method, we get to negative numbers. So functional properties, our products are solvents, ketals, which are used in a lot of applications. But you think about use as a biosolvent. If you think about your home, a lot of people have these air care diffusers. There are solvents in there today, and they get dispersed into your home. Some of them are aromatic solvents, some of them are, not so nice and friendly solvents. That's a tremendous application space where these solvents can have a home. Because of the double ketone bond, they have a preservative booster effect, so an antimicrobial properties. They're not an antimicrobial agent. I want to make that clear, but they do offer the supporting function. They're fully biodegradable, so you can use them into all kinds of applications. If they're leached out into the soil, eventually they'll hydrolyze and they'll biodegrade. As a skincare product, for example, there's a lot of products used, like silicones are being used there as a haptic and sensory feel ingredient. Our products can displace them, not replace them, because the silicones are tremendous good products, but they are what they are. And in Europe, and I think in the US as well, they're under ban. So the D5 silicones are being pressured. These products can actually replace them or displace them. And then also as a plasticizer in a lot of applications, like PVC, for example, they've been already tested and trialed. So they function as a natural bio-based plasticizer to increase your carbon footprint of the or reduce your carbon footprint of your vinyl, for example. So these are all the functional properties. There's a lot more that we can talk about. There's a lot of studies being done in the past, and we'll continue to roll out our capabilities, especially when the plant is coming on stream, which is end of 26. We're going to be full steam moving ahead with our portfolio. Any questions, just reach out and I'm happy to engage.
We do have time for one question.
Thank you. My name is Lisbeth Robinson. I'm with Lathrop GPM. Are you competing with alternative fuels feedstocks?
Yes and no. There is proven, there's a lot of articles and papers written about fuel additives. So they're not a fuel because it wouldn't be smart to do that. You esterification, you do a lot of processing, so it's not an efficient fuel. But there's data and evidence to support the, let's say, as a fuel additive, that they're very functional. Right.
Are alternative feedstocks,
Yep.
alternative fuel feedstocks using the same type of feedstock, in which case is there competition for the feedstock?
A competition for the feedstock, obviously, because a lot of people are looking for biomass, right? So there's obviously competition. Yes, there is competition. Let's face it, the world is only so big and we produce so much food and food waste and bio waste and agricultural waste. So yes, there's going to be competition, but that's why I think the point that John made earlier today is it's not going to be an or situation. It's and CO2 and waste, handling of bio and the recycling. So it's a combination of all these things that need to happen. But yes, the answer is yes, there is competition.
Great. Thank you very much, Jan.
Right.
All right, next up, I'd like to invite Hamilton Perkins to the stage.
Okay, this is a prop, by the way. All right, so hi, I'm Hamilton Perkins, founder of Hamilton Perkins Collection. We're recycling supply chain waste. First thing about me, a little bit, magazine recycling business in middle school, got shut down very fast, surprise, surprise, but didn't let that stop me. Went on to start making products from recycled materials. Found myself in this landfill here, getting really close to the problem. 400 million tons plastic, don't need to kind of go and hash it all, but got really close to this problem here, the PVC problem. Our company was making bags from recycled plastic and from vinyl billboards, et cetera. And, we just kind of asked ourselves, like, what if, could there be a better way to process it? So we're making organic acid using chemistry and biology and upcycling. So this is the process. So we're starting off very early, probably compared to a lot of the previous presenters here, but pre-treatment process, essentially breaking down the PVC, basically extracting the plasticizers, and getting to a point where we have an organic acid. That's just our very first test to get started, but our goals are to get all the way to something of higher value, such as a pellet or a yarn formation at a later step. The way we've kind of cut the market up for ourselves, we've said there's a ton of opportunity here for clients as well as corporates or partners. And we came up with this is a small number that we've come up with, but I think it can be much greater if we use a little bit of creativity. Basically what we're doing is we're out to help you turn your cost centers into profit centers. If you can think about the amount of landfill waste and similarly like the amount of material that doesn't get repurposed, what could be done with it. This is an example of what could be done with it. This is one of our bags made with pineapple leaves, PLA, PVC, and a bunch of other stuff. And so we want to reimagine kind of what happens at the end of life process. So this is how it's valuable. So we start with 2 revenue streams for ourselves. Basically, we start with taking waste. That's one pain. If you can think about all the waste streams, and this stuff starts to add up. It sits in storage, it sits in offices, it sits in kind of these discrete places. So first step, take that off a client's hands. The second step for us is to sell the pellets back to those clients or to other clients. And we've already kind of done this essentially with our bags. So far, we've generated $1.4 million in revenue from actual clients, selling bags, doing the offtake. And so now we're just applying a slightly different process to get to that point. So we're the team to do this. Just from a backing standpoint, most of our work was bootstrap, but we did get an investment from Pharrell Williams, which gave us a huge boost. We got into something called Lab Start, which gave us a scholarship from Department of Energy and attracted some investors like Hewlett Packard, et cetera. And more recently, we were in Techstars. So this is our team. So our CTO, Idris, is running everything in our lab. We're down in LA, so just got started with our initial processes. Annie on our team is doing business development. Percy works very close with our tolling potential partners and LCA, TEA, and ultimately just how we scale up. And Rosie works with fashion and performance, making sure everything actually does what we intend for it to do. So right now we're working on securing partnerships, expanding our labs, and essentially scaling production. So what we would like to propose is, if you can think of waste streams that you have, whether it's specifically of PVC, so it could be anything in your organization, we would like to have a conversation so that we can see how we can work together. So this is how we plan to get to the next levels. This is our timeline. So we're down in Los Angeles in the Clean Tech Incubator. So we just got our bench space there now, and we're getting set up, ready to go. We can probably take on another 3 pilot partners going into the new year or going into next year. And from there, we look to kind of expand into wider scale pilots and partnerships. I've been Hamilton Perkins, and I definitely hope that together we can join this circular revolution, and that we can turn trash to treasure, waste to wonder, and make a difference together. Thank you.
Thank you, Hamilton. Do we have any questions in the crowd? So I'll start with a question. I think one of the challenges that's kind of touched on today and probably be touched on a little bit more this week is just how you deal with the additives and other parts during recycling of materials and how that might get incorporated into a new recycled product. How do you guys think about that and how you ensure the safety of what you are giving to the consumer?
Yep, thanks for that question. So yeah, like we're really early, but we have come up with a schematic that basically shows, some kind of very basic ways of extracting those plasticizers, getting to that zinc and getting that chlorine. That's the problem here, is those bonds with the chlorine. So we've come up with a way to address that and to basically get to a salt, and then that salt can then hopefully get us to like a carboxylic acid or similar that we could then create a circular loop with and make into something that's of higher value from there. So wish us luck.
Okay, thank you. Any additional questions?
That was great, Hamilton. Question is, you seem to be focusing on PVC. So my question to you is, how are you attempting to diversify what feedstocks you can work with? Because, there's a lot of scrutiny rightly being directed towards PVC. So are you thinking beyond PVC?
Yeah, that's exactly why we're here. I mean, we would definitely be open to looking into other feedstocks. We do see the potential to begin in the PVC realm, but we're open to other materials. When we were making our bags from recycled materials, we sold about 50,000 bags, and I think I counted up to about a dozen different kind of like either blends or types of materials that went into those bags. So we're no stranger to kind of diversifying material types, and hopefully we can have some conversations while we're here to introduce some of those pilots in our labs down in LA.
All right, thank you very much, Hamilton. Okay, excellent. Next up, I would like to invite Eric Steen from Lygos.
Okay, thank you. Pleasure to be here. It's my first time, so excited to meet you all and have the opportunity to have some exciting discussions today. Again, Eric Steen, I'm the CEO at Lygos, and really simply what Lygos is trying to do is build better materials for better products. I think the problem is ahead of us. This crowd really knows this, right? Everyone wants sustainability. Governments are mandating it, but you also have to have that cost performance basis. And I think the one that I'm most excited about right now is the chemical industry and the ability to innovate new materials platforms that can bring new performance qualities to the market. Obviously, it's a lot of big companies saying this, and I think from our perspective, right, everyone wants it, but without partnerships and without working together, we can't deliver it, and we need a massive step change in innovation really to get there together. So that's our mission, right? Lygos exists to help accelerate the world's transition to high-performance, sustainable solutions. Who we are, we're really a specialty chemical company, and we're targeting helping partners meet, again, both performance and sustainability goals. We bring in multidisciplined approaches to do this, and so this is best biology, best chemistry, and best application development labs, and I'll talk a little bit more about that. And then a mantra that we have is collaborate to accelerate. Again, to me, the problem's urgent, but if we don't collaborate and work together, we're not going to get there fast enough. And so this is something that we really strive to drive within our own company. And then finally, end goal focused, right? This is all about understanding what a partner or a customer is trying to solve. One level deeper about kind of what we do, what's this multidisciplined approach that we use at Lygos. So it all starts with identifying and understanding what the partner's trying to solve. What's the problem? What's the chemistry and performance innovation they're looking for? And then at Lygos, we have a vertically integrated platform to go from strain or catalyst development. So this is really simply taking waste sugars or feedstocks and converting them into the downstream monomers. Then we do fermentation scale up, as well as downstream processing and application development. One level, again, deeper, some of the partnerships that we've announced and how we collaborate to accelerate is shown here. And so starting with the market needs first, we like to partner with brands and big companies to really solve their problems. And then within Lygos, within our kind of vertically integrated commercialization platform, it all starts with our world-class team. And so we have amazing PhD scientists and polymer chemists that really work with other companies to get there faster. So strain development, we have a deal with Ginkgo Bioworks to get there faster. We have on the fermentation side, we just announced a partnership with CJ Cheljadang to get us there faster, and they're a massive fermentation provider. And then similarly with downstream processing. But I would highlight one of the areas where we're really uniquely and heavily invested is on application development. And so we have all this great technology and great capabilities, but I would also argue that to translate it into the customer problem is critical. And that's what our application development labs do. And so we have those built around the 3 target markets that we're entering today. A little bit more on the partnership with Ginkgo here on strain development. Again, it all starts with our world-class talent and technology. We selectively then deploy resources and partner with Ginkgo to leverage their automated laboratories. And so they have labs with billions of dollars of infrastructure to go and automate biology, right? So it's capital efficient for us and our investors. It enables us to get to market faster. And ultimately, that's our goal, right? Get to market fast so that we can drive sustainability and really pull it through on a product basis. A little bit about our business strategy. So we're end goal focused. So to me, again, this is, imagine we're in home care and looking forward to have discussions around this today, but and the rest of the week. But it starts with identifying the customer problem. We then design, develop, and deliver the solution. And we do this in parallel because, again, really simple, we want to ensure rapid adoption and product market fit. Okay, shifting gears now a little bit concretely about what the chemistry platforms that we have at Lygos today and what they're doing. Broadly speaking, they're replacing persistent and sometimes toxic chemicals. Satellis is a biodegradable polymer line that's based on polyaspartate polymers, and Ecoteria is based on bio-based malonic acid. In each case, strong market pull that we're seeing for performance solutions based on those. And then really advantaged process economics. So these are products that can be made from fermentation at very strong economics. And then finally, they represent a really rich and diverse class of chemistry that we can innovate upon in order to hit those performance metrics that partners are looking for. Satellis, so this is the biodegradable polymer platform. And it's high performance, it's sustainable, and it's multifunctional. And it's going into today 4 markets that we've entered. So we're already selling, we're already on ag fields, where really simply, because of the biodegradable aspect, it's nice because it's not contaminating the soils. But what it's doing for plant growers or farmers is increasing the growth of, or the return on their fields investment. So more food, less fertilizer. And it's enabling nutrient packages to really be used more efficiently at the root ball. In home care, for example, on just to give an idea of how I think about multifunctional, how do you reduce cost to a formulator? How do you make enzymes work better, following the cold water trend, and perhaps also eliminate some of the persistent products that are typically formulated and have whiter whites, no color fade, and all those performance characteristics that we want to have. And so we're showing that, we're demonstrating that, and we have some really good data around it. Ecoteria, again, shifting a little bit on the platform and what the chemistry enables. We're really excited about the growth aspect of the coatings market that this chemistry can enable, but it also has some exciting drop-in markets. So I'll wrap here, but I think really big announcement for us. And as we think about, how do you get to market? How do you really drive sustainability impacts? Well, we've lined up and signed and announced an agreement with CJ to build a biorefinery, a commercial scale biorefinery here in the US in Fort Dodge, Iowa. And when you really think about our announcement, right, this is commercial scale. So this is up to 40,000 tons per year of product that we can produce. It's world-class partners. So this is back to my collaborate to accelerate model, right? We want to work with best-in-class partners to get there faster. But both CJ as a leading fermentation provider and operator, leveraging their expertise, as well as Cargill on the upstream feedstock input. It's a sustainable footprint, and so this is, where in the U.S. the corn is just grown in a way that it's very efficient, and the site overall really provides an exciting growth opportunity going forward, where additional bioproducts and polymers can be driven through the supply chain and what we've lined up. I'm honored to work with an incredible team, and so you see company-wide expertise from some of the biggest consumer product companies, biggest specialty chemical companies, as well as others, and have Chantal, our Chief Sustainability Officer, joining in the room as well. And so look forward to speaking to everyone. Key takeaway, as you think about Lygos, we want to be the go-to innovation partner for helping you all meet your highest sustainability and performance goals. Thanks.
All right, we have time for one question. So I think one of the challenges in kind of these brand partnerships and some of the other partnerships you're looking at is IP. I know you noted that this was a strength in terms of your company, in terms of your IP, but it can be a challenge. How have you guys tackled that wide range of partnerships throughout your development while still protecting your IP as well?
Yeah, I think it's a case-by-case basis. And so again, kind of looking at the market first, there's specific applications where we want to enable wide adoption. But some partners really want to look at customization. And so the flexibility and the innovation on the material side of the platform enables a pretty broad swath of that. And so, I would say on one side, while we've announced a lot of partners, I think there's a lot of room to collaborate here, right? And carve out areas of interest to or for the right situations. But yeah, it's a great question.
All right, thank you very much, Eric. All right, excellent. So we have one last startup for this session before we have a little bit of a break. So I would like to invite up Ned Weintraub from NobleAI.
Hi, Sharks. I'm Ned Weintraub, Chief Commercial Officer for NobleAI. Quite a few of you know us, and looking forward to introducing us to a whole bunch of new folks. Huge thank you to Change for bringing us in. There's a lot we can go through, so I'm gonna keep this nice and tight and keeping you from the break. So what is Noble? Who are we? NobleAI is a company that dramatically accelerates product development, optimization for companies that are, whether you're energy, chemical, material science, both profitably and sustainably, really trying to drive very, very hard new product development and obviously optimization of existing products. We are a science-based AI platform that is cloud-based, extremely robust, containerized, and has the ability to really scale to the world's largest customers. And we do this today. This is not a pie-in-the-sky idea. We've been at this for 4 years, and we're delivering real huge savings and real leaps forward for our customers. I'm not going to explain the size of the chemical industry to you guys. You live it every day. But one interesting bit about this slide is that 96% of all products made in the US involve the chemical industry in one way, shape, or form. So you would imagine that this is such a fertile ground for companies like us that are science-based AI companies, and we're just, there's thousands of companies that are propelling this. The reality of it is, it's still really hard. This effort has been challenging because at the end of the day, the development in chemistry is slow, it's laborious. Deloitte had a great point in their 2020 write-up that, for the last 60, 70, 80 years, roughly, design of experiments is still the way that things are done, and it's plodding and it's slow. And IBM even quantified it by saying it can be, in the tens to hundreds of millions to create and optimize new products. So there's that, right? There's the economics of it. On top of that, now you have significant regulatory pressures, not just to create sustainable products, but also to go back and reformulate, right? Right now, Europe is pushing a tremendously aggressive agenda to really get companies to reformulate their extremely toxic formulations. So there's a lot of downward pressure there. And on top of that, there's upward pressure from the market, right? There's now apps on your phone that tell us, what is good and what's bad. My kids come to me every day with a new app saying, Dad, you can scan this and see what products are good for you and what products aren't. So there's both downward pressure and upward pressure from the market that's really driving this need. The challenge, though, is a lot of these companies, unless you're Procter & Gamble, who are doing amazing things, and one or two others, you're left in the, okay, let's just grind through this. And there's a tremendous risk, not just to profits, but truly to these companies and their ability to be commercially viable going forward. So where does Noble come in? Number one, Noble, as I said, we created what we think is a differentiated science-based AI platform, or AI for science. And there are two different aspects of our offering. One is a model build platform that allows us to work with our customers to build customized models using 50, 60, close to 75 different ways of building AI models. And what we do is we break it down, we break these problems down from these giant monolithic problems into sub-problems. And based on each of these sub-problems, there are different techniques that we use and deploy. A lot of that, probably 80 to 90% of that is automated in the platform and the model building aspect. So we can generate these customized models very, very quickly, but then we allow our customers and mount this on what we call our VIP platform. Not very creative, but it does stand for visualizations, insights, and predictions. And it's what you're able to do with that model that is incredibly powerful. It's, whether you're able to do DOE on steroids or inverse design with very precise parameter sweeps, really very, very sophisticated prediction methodologies with explainability. Try to get a scientist just to agree, oh, it's AI, it's going to work out, it's fine. They need explainability. And so for us, it's not just, okay, what happens in the lab? We need to be able to do this across the globe and really focus on how do we scale. How do we really bring this to our very large customers, but even small? We even work with startups as well, and do this safely and securely. We have an unbelievable range of ability, almost limitless in the types of applications and problems we can work with. But as you can see, all of these have sustainability issues. And so for us, that is a driver for us. That is our North Star, right? How do our customers be sustainable and profitable at the same time? And so as we go through, we certainly can, do one or two projects, but typically our customers, do 5, 10, 15, 20 projects on an ongoing basis. So at the end of the day, jokingly aside, and I said, you know, sharks, but we are a startup. We've been in business for 4 years. I like to say we're a 4-year-old, 2-year-old company. Started in COVID. And so the first 2 years were really academic. In the last 2 years, tremendous growth, doubling every year in our revenue. So we are backed by Microsoft, we're backed by Solvay, we're backed by Chevron New Ventures. So we do have a lot of energy, pardon the pun, but also you know, real motivation from our investors who are also our customers. It's a lot to unpack. So I am going to be here. I have a partner, Ethan Mirsky, who's also doing an event, I think on Wednesday. I look forward to talking with you guys throughout the week. So thank you very much.
All right, thank you, Ned. What questions do we have?
Homer Sway. The AI is definitely part of the future. The challenge not only is the amount of resources that go into it, but it's only as good as the data that goes into it, and most of the data is locked up.
Yeah.
In pieces. How do you go about finding the information?
Yeah, that's a great question. The reality of it is that most of our stuff, most of our projects start with a very limited aspect of the data, right? This is not an LLM. We are not ChatGPT. I probably should have started with that. But the reality of it is that in our world, there isn't a ton of data. And if it is, it's disparate. It's not in the right place. It's hard to get to. So we need to be able to really find ways of accelerating with very small data sets. And that's exactly what we do. So we've even started projects with as few as 50 to 60 rows of data, and really just gives us directional ability to go and know where we go next to find that data. That's the part of the process that we can really help accelerate. So great point, but it is an important takeaway. You do not need to rake the ocean filled with ones and zeros to get started with AI. You just don't. Don't listen. You can get started with a small amount of data, and if it's important enough, watch how fast people come to the table with more and more data.
Right. Thank you, Ned.
Thank you, guys.
Well, thanks, everyone. We're a wee bit over schedule. I'm sorry, Jenny. I tried, but just a little bit over. So I'm not going to belabor this. We have a break, a networking break coming up. Please leverage that to get better acquainted with these entrepreneurs that we have here. We're going to meet a second batch of them after the break. So before we break, just please join me in thanking our moderator, Cassandra. Wonderful job. And thanking our first batch of startups. Thank you very much. Welcome back. Now, at this point, we're going to go through the, I guess, our second half, or not quite half, but our second crop of startups. I'm going to be very quick here, and I'm going to hand over the mic and the emceeing to our second moderator, Alec Brewer from Ourobio. And I checked with Alec. Yes, they are an alumnus of our startup program. So that one I got right. So without further ado, Alec, the stage is yours.
Well, thank you again for having me here. It's an honor to be back in the room and back at Change Chemistry with you all. The last time I participated in this event was in fact a part of the startup showcase. I think we were called Ourobio at that point, and that was 2 years ago back in Philadelphia. Last year, my co-founder, Kobe, helped out in St. Louis. And again, we are extremely passionate about and excited about what goes on during the startup showcase and for Change Chemistry's support. I'm not going to go on stage because I can't possibly top everything else that Cassandra said. She did an excellent job earlier. And so I will just echo much of what she said and pass it over to our first speaker with 12. Ram, come on up.
Good afternoon, everybody. Thank you, Alec. Appreciate the chance to be here. Ramprasad. I've been with 12 now for 3 years as Chief Commercial Officer, but trying to back into a strategic advisor role, trying to advise multiple companies, but I'm still spending a lot of time at 12. 12 is a carbon transformation company. We use the word deliberately, carbon transformation, because we want to distinguish ourselves from folks who directly use CO2 for enhanced oil recovery or other applications. So we electrochemically, so using water, CO2, and renewable power, convert the CO2 electrochemically into products. So our brands, you'll see there, the products we make are all hydrocarbons. E-Jet is our sustainable aviation fuel. CO2 Made is the kind of consumer brand kind of products. You see the shoe there, appropriate for this venue. And E-Naphtha is our core product from which we make those CO2 Made products. That's the naphtha, sustainable negative carbon naphtha, as you'll see in a minute. And the core unit that we use, the electrochemical unit, we call the Opus. And all of these brands, we have great partners that we've made this with. We started our program making sustainable aviation fuel in partnership with the Air Force. And since then, if you look us up, you'll see we've announced agreements with Alaska Airlines, Microsoft, with more recently IAG, which is the parent company of British Airways. We made some ingredients that went, CO2 Made ingredients that went into P&G's Tide. Thank you, Todd. We also made some plastic auto parts, hard plastics that went into cars for Mercedes-Benz, and some sunglasses, some fun stuff with under the Pangaea logo. Our core plant is called the air plant because we're, in the future, we look at CO2 coming potentially from the air, and even now, I guess CO2 does come from the air. This is recovered CO2, and that's what an air plant looks like. So this is, products made from air effectively. And you'll see there that we've tried to schematically show what one of these units might look like. There's some internals that you see in the bottom left there, and one of them schematically. And that's what it looks like. To start with, we have a little unit that is the core of what we do. That's the membrane electrode assembly. So all of the electrolysis here, for those of you who are not electrochemists, happens on a membrane. So to give you a feel what that looks like, we started with membranes that look like a postage stamp, and our go-to-market size now is the size of a laptop or a foot by a foot. And so what we do is, so you'll see there, it's a polymer electrolyte membrane, and the black stuff in the middle is the secret sauce, the catalyst that we coat on it to make sure that the reaction that we want happens. So then each of these square cells are then basically stacked into making a stack. That stack, effectively, each of these cells gets the electricity it needs, the feedstock it needs, and the products come out of them. And then they are manifolded together and taken away. Our stack, market stack, is the size of, say, a dishwasher. And if you guys are in the area in Alameda, or we have a pilot plant that in California that has this stack under operation all the time. And you'll see that these stacks, many of these stacks are then put together to make our module, the Opus module, and which then goes into making the air plant. So we're building an air plant currently in Eastern Washington State, say, I guess, a couple of 100 miles as the crow flies from here. And Moses Lake, Washington, that's where our first plant's going to be. It's going to make, commercial volumes of jet fuel and naphtha. Those are our core products. How does this work? We see our technology is sort of like industrial photosynthesis. So it starts with CO2, water, and renewable power, much like a plant does. And then the CO2 is broken down into carbon monoxide, the water into hydrogen, those products, and then get combined to making synthesis gas. As chemists, you'll be familiar with that, which then goes through a Fischer-Tropsch process to make longer chain hydrocarbons. As you guys may know, you get a range of products with Fischer-Tropsch synthesis, and our core products are jet fuel and naphtha. And so those are the products we are trying to commercialize, and we have commercialized. Just sticking with naphtha, which is sort of more interest with the change chemistry event we are at. This is what the carbon footprint looks like. It's a negative carbon footprint. Effectively, if you think about fossil naphtha, it starts with a positive footprint. I mean, that's nominally 0.7 kilograms here of CO2 per kilogram of product. That's primarily because you have some CO2 associated with from the wellhead all the way to processing of the fossil fuel to make the naphtha. We start with this big negative number. The negative number is what the amount of CO2 we consume to make a kilogram of naphtha or jet fuel. And then we add a little bit of positive footprint, and that primarily comes from the fact that even renewable power, if you're honest, you'll give it some footprint, things like making wind turbines or solar cells or whatever. And so then you end up with this negative 2.8 number. And so you look at the two, you get about a 3.5 kilograms reduction in footprint. And the naphtha that we make looks the same, in fact, is cleaner, doesn't have sulfur, metals, and we've done the analysis with petrochemical companies, and they've analyzed our naphtha and agree that it is perhaps even higher grade and maybe delivers better quality products when put into a cracker. And it looks, and you can see there, it's highly paraffinic, and it's a great feedstock for petrochemicals. We're well funded. We're not a star. We've been around for 10 years, and we've raised nearly $1 billion, some of it for future projects, not quite. And you'll see some of the customers that we've signed up there. We've got a suite of investors who are supporting us, and a large team as well, based mostly in, or the labs are based in Alameda and Berkeley, California. And our first plant, a small one really, is in Washington State, as I said. We're really excited. We think that 10% of all CO2 emissions in the world come from the manufacturing of such products. And our CO2 could be a great way to solve part of the problem. I agree, recycling and all the other things, biomass-based products are all part of the solution, but we can contribute. It's scalable as well. Long term, we really see this as air from air. We hope CO2 capture from direct air capture from air works competitively, and that's the CO2 source, and that limits, puts no limit on the scaling of our technology. So that's the hope as we're making these products from air. That's all I had. Happy to take questions.
All right, we have time for one question. Any from the crowd?
Hi, I'm Avery with Solugen. I wanted to ask, I know you guys have been very successful in terms of getting project equity financing for the facility that you're building out in Washington. Can you talk a little bit about what it took to get the right commercial offtake contracts in place to be able to secure some of that financing? I think you guys have overcome a hurdle a lot of companies are still dealing with.
Yeah, it's not easy, obviously. I mean, you need an offtake agreement, a long-term offtake agreement. You need someone who's willing to sign a 10, 12-year deal, because that's what your banks or other investors are looking for the project. And obviously, the economics that make sense. We have a lot of support through the Inflation Reduction Act and through other things on production of the hydrogen, production of the carbon monoxide, CO2 capture. There's lots of incentives that help the economics, but it's been primarily because we've got a long-term contract. And I got to say, that's a little difficult with customers who have small budgets. They're not willing to sign up for long-term contracts or are worried that you you sign up with us and then somebody else comes up with the next widget that's better. So you have to build in somewhat flexible contracts, flexible enough that the customer signs and inflexible enough that the financer then is willing to give you money. So yeah, we've been lucky. We've got, we haven't yet announced a contract on the naphtha. We've got contracts on the jet fuel. And as you will know, all of this is entirely voluntary. At least in the US, we've got some carrots. In Europe, you have some mandates and stuff that are helping as well bring customers to the table. But hopefully there'll be customers on the plastic side who say, hey, this is a great technology. We needed this in our portfolio, and sign long-term contracts. Good question. Thanks.
Yeah, excellent question. And thank you, Ram. Great work.
Thanks. Appreciate it.
All right. Well, as Ram very humbly mentioned there, 12 has done an excellent job raising nearly $1 billion in funding and being, I think, one of the later stage startups here, second only to Battelle, though self-recognized, not a startup. But next, I think we're going to one of the earlier startups that's joining us today, and that's going to be Praio and Advait. If you could join us. Good to see you again.
Hi, everyone. My name is Advait, and I am the CEO and founder of Praio. And I founded this about in March. So yeah, so still very, very early. So I'm going to be talking about how we can reimagine how we do biomanufacturing. So a little about me. I did my undergrad in chemical engineering from IIT Delhi, then went to UCLA to do my chemical engineering PhD. And now I'm commercializing that work at Activate Berkeley and Cyclotron Road. I also have Samanvay Srivastav, a professor at UCLA as a scientific advisor, who's a real material science expert. So conventionally, biomanufacturing is done in one of two ways, either by using the entire cellular body to do those conversions, or by extracting the catalytic part, the enzyme, and using the enzyme alone, right? And both have their advantages and disadvantages. Is that if you were to just use the cell, you can have very efficient multi-step cascade reactions. And a classic example of this is going from glucose to ethanol, which is a 10-step reaction, so a fairly complex reaction, right? However, this comes with its own processing restrictions. Let's say you wanted to make something like butanol instead of ethanol. Now you're going to struggle with toxicity. And in general, you're going to be struggling with mixing, you're going to be struggling with providing enough oxygen to the cell, so on and so forth. All of these challenges are related to keeping the cell alive. On the other hand, if you just had the enzymes, those enzymes are not alive. So you have a lot of processing flexibility. And an example of this could be high fructose corn syrup, right? However, now you miss out on that cellular environment, which makes it possible to have those very efficient multi-step reactions. So the crux of the problem is one is too complex and the other is too simple. So how do we bridge this gap? Like, how do we move forward? So to move forward, we actually went back to our biology textbooks. And if you remember from them, there are all these different organelles, like the nucleus, the mitochondria, all these compartments within the cell. And we thought, what if, instead of just extracting and using enzymes, what if we could mimic and utilize entire organelles outside? And that is what we have done with artificial protocells. So I'm showing you a vial of artificial protocells, and those squiggly lines in the schematics, those are cheap, commercially available polymers, which encapsulate enzymes in near-native environments. And because of this, we have the best of both worlds, right? We have this basic machine. So in terms of process flexibility, we have that from the cell-free aspect of this, and the multi-step reactions we have from the cell aspect. And so just to dive into more details, these self-assemble in milliseconds. So I can literally make those in front of you right now with our patent pending process. They have high interfacial stability, so they are stable for more than 4 months. They are toxin resistant, and I've checked this with different alcohols with very high salt concentrations, because fundamentally, this is a very simple machine. They are also easy to recycle because they are on the micron size. So that's why you can separate them with a membrane or simply, centrifuge, redisperse. And that is critical in terms of reducing your catalyst cost, because that is what is really going to affect your overall metrics. And finally, because we maintain those near native environments, we have shown rate enhancements for individual enzymes by more than 10 times. And if we co-encapsulate enzymes, which we have done, and have multi-steps reactions, we have shown orders of magnitude increase. So this is a new platform or a new paradigm of doing things. And I know I've skipped over a little bit of the material science here, and I'll be happy to discuss that. But this is coming from advances in material science and synthetic biology meeting together. So I can take this towards like pharmaceuticals, fragrances, and whatnot, but I really want to push this towards having a positive climate impact. And for that, I want to convert aqueous ethanol to higher alcohols. So the reason for choosing ethanol as a platform chemical is because it is the most widely available bio-derived chemical, period, right? And so by converting aqueous ethanol to higher alcohols, we are agnostic to how this ethanol is made, allowing us to support existing as well as emerging infrastructure. So this ethanol can be made by diverse biomass sources, corn grain, flue gases, waste, so on and so forth. As long as you can ferment it and get to an ethanol, then we can upgrade it. And the reason why I want it to be fermented is because that ethanol is aqueous or non-distilled, and 70% of your energy cost, at least in converting corn grain ethanol, goes into distilling it. So by converting it to a higher alcohol and having larger carbon chains, we can circumvent that. And finally, this is uniquely possible with protocells because of, again, the toxin resistance, because of the recyclability, the multi-step reactions, and also because we are doing this in an aqueous media. It will be very hard to use an inorganic catalyst to do this. So what is the impact of these higher alcohols? So of course, we can make sustainable aviation fuels with these at a lower cost from the alcohol to jet or ATJ route. And we have some preliminary numbers on this using Aspen simulations. But the point is, if you have a larger carbon chain, it reduces your dehydration cost and your oligomerization cost. These can also be used as higher blending for gasoline. So currently it's E10 and E85, but E85 requires like new engines. You can blend higher percentage alcohols. You can make common intermediates, which can be used for paints, resins, coatings, so on and so forth, for which ethanol cannot be used. So this is really diversifying what your biomaterials can be used for and have like greener supply chains. And finally, because we are doing this enzymatically, we have control over the chirality and the structure. So we can also go towards specialty chemicals and like, fragrances, pharmaceutical precursors. And if anything, biomanufacturing history has taught us, we should go from the bottom up here and not from the top down because of the margins, right? So currently this is at a 1 liter scale from my PhD work. A key part here is the control on the protocellular composition. So we have flexibility not only on the types of enzymes, but also on the types of polymers. So I have done high throughput screening methods. So I have run like more than 5,000 protocell compositions, tested them. And so we can keep evolving and optimizing that protocell. And the goal is by the end of 2025, be at a 300 liter scale. For this, I am working with the Lawrence Berkeley National Lab, and they have the Advanced Biofuel Bioprocess Development Unit, which has that mid-level infrastructure and the expertise to scale. And by 2027, hopefully at a pilot. So again, I am commercializing this out of my work at UCLA. Very, very happy to be supported by Activate Berkeley and Cyclotron Road, which really gives me the space to actually go ahead and build something real, right? And instead of just running forward with, raising money, building, raising money, building. Again, very happy to be part of Change Chemistry. And I'm currently looking for any advisory people who can advise me through this journey, and also for any early markets that we can target using these, using this platform and really demonstrate it there. So with that, I will stop and will be happy to take questions.
And I think we have time for 2 questions here. So anybody in the crowd?
Thank you. Thank you. It's very exciting and amazing presentation. I just wonder, now you're focusing on converting ethanol to other alcohols. if you need to, if you, let's say, want to target a different molecule, like what it takes to change the mix of the protocells. Like, if you can elaborate a little bit more about the science and technology behind it, please.
Right, right. Thanks for asking that. Yeah, so these polymers are charged, they are electrostatically charged, and they self-assemble because of Coulombic interactions in water. And so they are both positively and negatively charged. And enzymes typically have a heterogeneous surface charge. So enzymes spontaneously partition within these polymers and stay in them. So that's why we have a lot of flexibility in the type of enzymes we can use. So let's say we want to implement a different pathway. Those enzymes are typically going to be charged and sequestered in the polymers. So the optimization we would have to do is some part on the polymer chemistry, some on the enzyme variant, some on the pH, and then that's how we'll do the optimization. Yeah.
Thank you.
Yeah.
Time for a second question. If not, I have a follow-up. So a follow-up. We do have a lot of material scientists in the room, I believe. Can you elaborate a little bit more on the polymerization or the composition of the protocells, and kind of following that also? Can you tell us a little bit more about the enzymes themselves? You know, if and how you're making them, and you know,
right.
The either value chain or innovation that you're doing there.
Right. So on the material side, so these are complex coercivates. These are the phases, and it's a very broad field. People have done a lot over there. There are a lot of different polymers which form these phases. They could be any kind of charged polysaccharides, polyacrylic acid, PDAT-MAC, a lot of different polymers, so cheap commercially available polymers. Our main IP is regarding the surrounding the interfacial stability, the greater than 4 month stability, which allows us to make an emulsion out of these phases, because without that, it's very hard to stable at all, like maybe a few hours, those emulsions. So that's our like real progress there. On the enzyme side, for that particular application, those would be cheap, like commercially available enzymes. That's all I'm gonna say.
Well, you're doing great work. Thank you so much. As you saw, we shook hands at the beginning and just had the chance to meet at the ABLC Next conference last week. I'm going to say the same of Kelly with Oleo here, who did an excellent job in her presentation last week, and survived and thrived in the wolf pack, which is an extremely uncommon happening. For anybody that doesn't know what that means, maybe Kelly will take the chance to tell us. If not, I'll try and do so later on. But Kelly, please take the stage.
Hi, well, thank you so much. My name is Kelly Redmond, and I'm one of the founders of Oleo Sustainable Palm Oil Solutions, where we transform biomass waste into sustainable oil products. Conventional oil seeds such as rapeseed, palm, and soy are embedded across our global supply chains. And as you probably know, demand for these oilseed products is only increasing as applications expand from consumer goods and industrial applications to feedstocks for the biofuel sector. Nonetheless, these oils are extremely environmentally destructive due to the land clearing processes that occur at the beginning of their supply chains and can often result in very carbon-intensive end products. Perhaps the most notorious of all of these oil seeds is palm oil, as its production begins with the deforestation of high conservation value rainforest. Nonetheless, as you can see from the graphic here, palm oil is actually one of the most land-efficient oilseed crops. And if we were to shift demand away from palm oil to other vegetable oils, we would actually need more arable land to fulfill demand for oilseeds, and we would shift deforestation practices to other regions of the world. So this really elucidates the complex oilseed landscape that we operate in, wherein very land-efficient crops grown on high conservation value land are only balanced by land-intensive crops grown in less environmentally valuable regions of the world. We at Oleo believe that this entire ecosystem is ripe for an innovation that takes arable land out of the equation entirely and can produce non-food compete oils while preserving our natural resources and reducing emissions. And that's why we're developing a technology that harnesses untapped biomass waste to produce low carbon oils without the need for arable land. And our process really begins with biomass waste. We can leverage a wide range of feedstocks, everything from food waste to waste produced via bioremediation processes. We then take this biomass and put it through our microwave hydrolysis pretreatment process, wherein we subject it to very high temperatures and pressures to extract fermentable C5 and C6 sugars from the biomass. These sugars are then used as a substrate for the fermentation of an oleaginous yeast strain, which we ferment to the point of lipid accumulation. And the lipids that form can serve as a high-quality oil feedstock across a variety of different market applications within the oleochemical and biofuel sectors. Within the oleochemical space, it can be derivatized to form ingredients for a variety of consumer goods and personal care products. And within the biofuel space, it can act as a general oil feedstock for the production of sustainable aviation fuel. One of the really cool things about our process is that we can leverage a wide range of biomass waste feedstocks. Our microwave hydrolysis pretreatment process is capable of valorizing any source of biomass, lignocellulosic or cellulosic biomass that has a carbohydrate fraction of 60% or higher. And this flexibility is really matched by the metabolic flexibility of our yeast strain, which can metabolize both C5 and C6 sugars to produce a lipid with a fairly consistent fatty acid profile. To date, we've valorized 19 different sources of biomass across our end-to-end process across 3 different sectors: forest residues, macroalgae, and food and agricultural biomass waste streams. The biomass with the highest valorization potential within our process thus far are primarily within the macroalgae sector and pumice from the winemaking industry. This feedstock flexibility really offers our product both sustainability and supply chain advantages over other companies that are operating within the fermented oil space. They will typically leverage feedstocks shown here on the slide that are either food compete and result in a higher carbon intensity, or their process will be tailored to a very specific source of feedstock, which can prove problematic and bottleneck their supply chains should that feedstock become unavailable due to seasonality or other logistical issues. By having the ability to leverage a very wide array of biomass waste as feedstock, we can produce an oil that's truly non-food compete, and we can weather supply chain issues and maintain our supply chain stability. Our end product is primarily comprised of palmitic, oleic, and linoleic acids, and it has a fairly consistent fatty acid profile similar to that of crude palm oil. Over the next year, we'll continue to optimize it to be a drop-in replacement for crude palm oil within the oleochemicals sector, and it can be derivatized there into a variety of different ingredients, as well as a general oil feedstock for sustainable aviation fuel production. And to that end, we're planning on entering the market as a palm oil replacement within the specialty oleochemical space, and then eventually scaling to the biofuel sector as a feedstock for the production of SAF via the HEPA process. Altogether, we estimate that our technology, if commercialized, has the potential to abate 1.64 gigatons of Scope 3 emissions annually while serving a $19.5 billion market. We're planning to position Oleo as a B2B IP company so that our technology can connect biomass waste producers with oil consumers and enable a circular supply chain. We work with organizations that generate biomass waste to valorize those waste streams and transform them from something that they typically have to pay to dispose of into a feedstock that they can sell on the market to co-manufacturing partners within the oleochemical space. With these partners, we license our technology to them so that they can produce sustainable oil feedstocks and derivatives for both the energy sector as well as product formulators within consumer goods. We have a lot of really exciting early traction with both feedstock suppliers and potential customers. We're currently producing oil samples for compatibility testing with the consumer goods sector in a laboratory setting, and we have 3 waste valorization projects in progress around macroalgae and pumice from the winemaking industry. We also have 2 material transfer agreements in place with potential technology licensees. We're currently operating at the 1.5 liter fermentation setting in the lab. And over the next year, we're also partnering with the Advanced Biofuels and Bioprocess Process Development Unit, similar to Advait, to scale our process to the 300 liter setting. From there, we'll scale it to a pilot demonstration in June of 2026. To that end, we're currently seeking partnerships all along our value chain to work with us as we optimize and scale our technology to the pilot setting. We're looking to partner with anyone from biomass waste producers who could provide feedstocks into our process, as well as chemical manufacturers who might be interested in licensing our technology, as well as consumer goods and biofuels producers who could potentially act as offtake partners. This is the Oleo team. My co-founder, Gabriella, and I are not only really passionate about the work that we're lucky enough to do at Oleo, but our backgrounds do lend themselves well to building and scaling an early stage biotechnology company. Gabby has a background in new product development with specific expertise in process and manufacturing engineering, which will be really critical to us as we optimize and scale our technology over the coming year. My background is primarily operational as an environmental science and engineering officer in the US Army, overseeing large-scale technical operations, both domestically and abroad. And so that will be really helpful to us as we look to build out our value chain. We're also lucky enough to be supported by a wide range of programs and accelerators, both within industry and academia. And in particular, we're also excited to be part of the Advait and Cyclotron Road Fellowships program, which is what is enabling us to integrate into Lawrence Berkeley National Laboratory and leverage their expertise and infrastructure to scale our technology over the next year in a very capital efficient manner. That is all I have for you today. Thank you so much for your time and attention, and I look forward to your questions.
And one in the back. We have time for about 1.5 questions. And great job there, Kelly, working through winds of change.
Sorry, this is probably a pretty boring question. So I'm in the regulatory space, and I was just curious, have you identified CAS numbers for these products? And do you anticipate like regulatory hurdles as you move from like the bench space into a commercialized area?
Yeah, so I think that largely, no, we have not identified CAS numbers for our products. I think the regulatory pathway will largely depend on the kind of specific application and the partners that we choose for our pilot and how we commercialize it. So that's something that we're exploring in the coming months as we try to solidify our partnerships and really flesh out our pilot program so that we have the best chance of really launching and commercializing afterwards with a licensing agreement. Great. Well, thank you so much. If anyone has any other questions, feel free to come find me after this.
Kelly, we do have one more if you.
Oh, is there time?
Quick one.
I just have to stop speaking halfway through my sentence, I guess. So I just wondered if you didn't give us any yields or anything. Would you care to comment on which step is the least efficient and how much waste you're creating through this process versus how much you're actually consuming?
Yeah, that's a great question. So our specific yields, and we kind of define that as the grams of oil per grams of biomass put into our process. So it kind of ranges depending on the biomass that we're starting with as the feedstock, but we've gotten yields as high as around 30%. And to hit technical benchmarks within our techno-economic analysis to prove out the economic viability of this at scale, we need to hit 45%. So we're still within kind of that optimization range right now.
All right. Thank you, Kelly.
Great.
Yeah.
All right, well, Damon a few steps ahead, but thank you for taking the stage. We have 2 more startups left in this session, and this will be, well, Damon with A2O Advanced Materials.
Thank you. Great, thanks a lot for the introduction. Also, thanks to Change Chemistry for organizing a great event. I really liked how the keynote today really set up a lot of the opportunities we have for more sustainably using materials. At A2O, we're really focused on creating products that work better, safer, and longer. And how we're going to do that is by changing the way we think and use bonding materials. And that's where our tagline, Transforming Adhesion, comes from. So A2O Advanced Materials, we're a materials innovation company. We're headquartered in Vancouver, Canada, and we're creating these new dynamic bonding materials that reduce product failure, improve performance, and eliminate waste in high impact industries. And the really important thing here is how dynamic bonding materials will change how we think about adhesion. So to take a step back and say something super obvious, of course, every product relies on bonds to both maintain its function and perform whatever it's needed in whatever sector. But what we often overthink, or what our expectation is that these products are going to have a short and limited lifetime. And what we like to think at A2O is like, why is that the case? Why do products have a short lifetime, and how can we extend those lifetimes? So what we're focused on is applications where we can not only improve performance and reduce cost, but have a transformative impact on sustainability. This is, of course, an imperative. That's kind of why we're all in the room. And in particular, in the adhesion industry, there's been a somewhat of a lag in innovation that has caused us to need new solutions to solve, I guess, the new problems that we're facing in today. So when you think about classic adhesive materials, these are things like epoxies, polyurethanes, acrylics. Most of us are probably very well known with these. These technologies have been around for over 80 years. They're undoubtedly excellent chemistries. But when we think about those materials, they have some failure modes. They can fail in wet conditions. Over time, they might age and stress crack. And what some of the limitation here is that those products only form bonds during curing. And so we kind of can think of it almost like a single-use material, because if you deploy the product and something happens to it, it's not able to recover any of its properties, which could have disastrous consequences for the product. When you think about the product, once it's deployed, it's actually undergoing a lot of different environments. It might be going hot and cold, there might be vibration. So what if we had a material that had dynamic bonds that constantly change and self-optimize with their environment? What we've developed at A2O is a completely new material class. For the chemists, we call these aminopolyolefins. And these materials are enhanced when in wet conditions. They're flexible and cohesive, so they avoid stress cracking. And these dynamic bonds actually are what gives us this reversible property. And this reversible bonding property is what enables the material to regenerate its properties over time by changing with its environment. We could also leverage this to reuse the material, as well as enabling recycling pathways. So I've been talking a lot about dynamic materials. What does that actually look like in the bulk material? The first key differentiator of our material is they stick to virtually every substrate, including even classic non-stick materials. So this is us sticking between between two pieces of PTFE or Teflon, classic non-stick material. No commercial adhesive can stick to this. These materials are also autonomously self-healing. What this means is that the material is cut, broken, or undergoes some type of mechanical shear stress. Those dynamic bonds, if recontacted, will autonomously refuse, re-entangle, and you get restoration of the original mechanical tensile properties. These can self-heal in as little as 20 minutes. This is valuable because if you're using this as a coating or adhesive, obviously, as we've talked about, the product's going to change. Things are going to happen to that bonded joint, but the dynamic bonds are actually going to be regenerating the bond strength over time, and in this case, regenerating the adhesion force. Finally, not only are these materials waterproof, they could even be applied underwater, which is, again, another key differentiator from conventional adhesives, and no material can really combine these four properties. So what our core technology is a new way to manufacture, or I guess produce these materials. Again, for the chemists in the room, these are aminopolyolefins. The important thing to note here is we can take olefinic feedstocks, aminate them to put on these potent dynamic bonds. Our process is scalable, low waste. We use abundant feedstocks to form these high value add products. We kind of have two main material streams right now. Within the additives, we're enhancing other products. We're also developing entirely new products, which are tapes and coatings. So with respect to the additives, this is kind of our go-to-market. Of course, the fastest way is not just to replace all the products, but actually to enhance them. So here we've got about 7 MTAs underway, we're doing some joint development with some partners to create some better, actually optimize their products. So some of the areas we're working on are tougher thermoset adhesives, rubbers with better recycling potential. And we don't see ourselves as ultimately a huge manufacturer of these materials. We're a materials innovation company. So we're scaling to a certain level, but then going to license out to our partners in specific fields of use. But kind of turning the page, instead of just enhancing the products that are already on the market, we want to bring kind of our transformational product to market. And this is our coating and tape product. So by taking essentially our resin and making full formulated products, we really capture those new unprecedented combination of properties. We can solve challenging bond problems to bond kind of unclueable products. This self-healing and regenerative property actually enables the product to extend its lifetime. And again, these are very underwater, are very resilient underwater. So these might look like pretty different applications. We're talking about things like marine coatings, anti-corrosion coatings. We're also talking about apparel. These are applications that are actually united by the challenge of underwater bonding and challenging substrate bonding. And yeah, I gave Nike a shout out because happy to be here today. So we're kind of working on those problems first with our partners, but we do see this as a platform technology. We see a lot of opportunities on the horizon. These are, of course, more complex problems, but when you think about what we're going to need for actual direct air capture, or what we're going to need for better batteries, we need batteries that don't fade. We need direct air capture that has better efficiency, larger scales. These are still fundamentally bonding problems. And when you think about these technologies, I can't guarantee it'll be ours, but I guarantee that we're going to need the same innovation in bonding chemistry to enable and use these products, especially when it comes to using resources more sustainably. When you think about how many batteries we currently dispose, that's an issue with battery binders, right? A much more inexpensive component than what's actually doing the active work in that product. So with respect to, or a little more about us, we've got a pretty robust IP portfolio. This technology is originally out of the University of British Columbia in Vancouver, Canada. Our IP portfolio kind of spans from the core technology, the catalyst, materials, including composition of matter, applied fields of use. This is a pretty robust and extensive portfolio. And our first patents have started to issue, and we've got a lot of other applications around the world. With respect to the team, Natalie and myself are joining today. We'll be in the networking events later. I'll also have some of the material if you want to come and stick with us. The important thing here is we are still a small team, but we're very committed to solving these big challenges. And we've got a lot of very specific expertise in catalysis from the chemistry side, as well as chemical engineering to understand how materials flow and age. So to kind of wrap up, we're kind of between funding, so I guess I didn't include that other slide, but what we're looking to get out of the conference is we're always looking for more partners. We are solution seekers. We want to find people that are having bonding challenges. Yeah, I guess was that probably good? Yeah. Thanks a lot for your attention and happy any questions. Yeah.
Yeah, awesome work there, Damon. A great presentation. We have time for one quick question.
Hi, very interesting. I'm just wondering if you have had the opportunity to test the bonding on actual articles from customers, so like real parts and the surfaces and shapes and sort of complexity that comes with the actual applications.
Right, specifically in the apparel industry or kind of at large?
At large.
Yeah, so at large, we've got real world evidence of, like in the marine case, we've had samples that have been in the ocean for now 5 years with no loss of bonding, sticking things like Teflon and metal underwater. In the apparel, we're working with a couple different partners. There's kind of an application around footwear. We're also got a wetsuit application to make wetsuits that seal better, which I still think is an unsolved problem.
Thank you.
Yeah, thanks a lot for your question. Appreciate it.
Yeah, thank you, Damon.
Next.
All right, well, we'll move on to our last presentation, part of the startup showcase today. And Isaac from Human Chemical, if you could please join us on the stage. I can't really clap, but let's clap for Isaac. And his partner.
Okay, hey everybody. Thank you for sticking with us here till the end, and thank you to the organizers for accommodating our special request for a demo. Let me know if this is perfect. Okay, excellent. Hey, so I'm Mattson. I'm a co-founder and CTO at Human Chemical. This is Isaac.
Hey everybody, Isaac Wilkes, co-founder Human Chemical.
Yes. We are fundamentally an in silico chemical hazard assessment company. So we build machine learning models to predict chemical hazard directly from the structure of a compound. And we are really proud of our product. I think it's pretty cool. It speaks for itself. So we're going to let it do some of that speaking. Just going to get through a couple of slides to kind of level set on what we're talking about first, and then we'll get into demos and hopefully some interaction. So with chemical hazard assessment, the challenge really is understanding how some chemical compound interacts with the body or the environment, whether it's a new chemical or it's a chemical on the market that we just don't have much data for. So this is the challenge we're tackling. So the current approach, I think most of us have probably heard of read across, right? Or structure-based read across, where we have some mystery compound here, which is not a mystery in reality, but it's a mystery to us right now. And if we're trying to get a feeling for how this compound might behave, what kind of toxic properties it might have, if we're using read across, we would look in our library of existing chemicals that we have information about, find one that is very similar, such as this one, which is just one atom different. And we would look at basically that tox profile and then make the assumption that the new compound, the compound of interest on the left, is going to behave similarly. So here's an example, right? If you go to PubChem or something, there's like tox profiles or hazard profiles. So the reference compound here is acute in animals at high doses, no other tox alerts on PubChem. So we might think that the compound of interest on the left shares this tox profile, but I think as many of us who have done read across before know, this doesn't always work. It turns out that this compound, even though it's only one atom different, has a substantial tox profile that's not captured by the very similar compound. So what we really need is just a more direct approach, right? Read across is really operating in like a proxy space for what we care about, right? Structure is not, what we care about is the properties, not the structures. So what we do is basically allow you to, instead of reading across, you can just direct read up the properties from the compound that you're interested in. So it also would let us do something that we might call activity-based read across, but we'll get into a little more detail soon. So let's do a demo. See what this looks like in real life. So we have a demo here. This is what the tool would look like. You could, if you were a chemist, you would, get an API key from us or a key from us, log in, like so, and you would be presented with a screen like this. And let me go grab a sample compound. So here is the SMILE string. I assume most of us know what SMILE strings are. It's a way of representing chemicals in text. So we'd paste the compound in and click predict, and a couple of things are going to happen. So first, we can verify that we're looking at the compound that we're interested in. Our suite of machine learning models is going to basically make predictions for a variety of endpoints, variety of basically hazard endpoints, and then over here, we'll get to this part in a minute. It's going to allow you to basically like chat with the model and chat with the literature about your compound at the same time. So what we're looking at here, basically per column, is obviously, we have an endocrine activity. We have all these different kinds of activities in various bodily systems. Our models are going to tell you whether we think they're active, possibly active, or inactive. The probability, I think this is fairly straightforward, but something that's not so straightforward, but is crucial for turning in silico predictions into actions, is a confidence score. So what we report to is we just give you a confidence score. It scales between 0 and 1, and basically the predictive performance of our model scales perfectly linearly with this confidence score. So if the confidence score was 0, basically the model would be guessing. Okay, don't trust that prediction. If the confidence score is 1, our models have an average F1 score of 0.9, which is like basically saying that we have very high true positive and true negative rates and very low false positive and false negative rates. So these are we'll emphasize again, these are very powerful, very modern predictors trained with methods that were only developed in the last like 6 months to a year in the machine learning literature. And so we also allow you to chat with the model and collaborate with it. So by default, it will produce this explanation of the compound. It's going out on the internet, it's searching, it's not just ChatGPT, it's a kind of series of models that are kind of hyper-tuned for chemical tasks. And something that we also are finding that customers are really interested in is, with read across, we have typically 2 compounds that we are looking at the source and the target maybe. So we also have the ability to compare compounds directly. So here is the read across, the one that we would have found as the target versus the one that we were interested in from the start. So it's generating these predictions, and it's very easy to compare these 2 compounds head to head. So if you are making a decision about which compound to use, it's easy to kind of get a rough sense for which might be less toxic or less bioactive in a variety of our bodily systems. So there are a few questions that routinely come up when we present our work, and I think I'll answer those, but then it'd be great if we could go into like a quick, if anyone has like a compound that they would like to run through the tool, this is a freebie, so think of it, I'll answer these questions. And then we can maybe take one of those. So our data comes from, so there was a great, I think someone mentioned earlier about the quality of the data is really going to dictate the quality of the models. So we train our models on over 700 assays, basically from EPA ToxCast. So it's vetted and curated by the EPA. And so it's very high quality data. And what we're predicting is activity. It's not necessarily toxicity, it's activity. It's answering the question, if this compound is introduced to some biological system, is it going to affect how that system behaves? Yeah, we validate our predictions. So in a standard kind of machine learning way, we'll validate our predictions on only compounds the model's never seen. We want to be fair. So when I mentioned that 0.9 F1 score, it's only on new compounds. So I guess now it would be, it's always interesting to see what people are thinking about, but does anyone have a compound that they're, or a chemical they would be interested to run through this of any kind? I'll just search for the smile string and put it in. BPA, yeah, that's it.
And as you're starting this second phase of the demo,
yeah,
would you like other questions as well?
Yeah, sure.
Okay, great. All right. Anybody in the crowd have questions?
Is this okay? One of the cool questions I have as we get into the predictive toxicology space is a lot of the models are good at discrete chemicals. Do your models predict polymers, like for these smiles codes and things?
Yeah, so they don't predict polymers per se, but it doesn't need to be one discrete molecule. So this handles salts, this handles kind of pairs of compounds. So not necessarily whole formulations, but yeah, you can add salts in there, you can pair compounds up. Yeah.
Thanks.
And a quick follow-up to that, synergistic effects as well?
When there's 2 compounds present, yeah. So we train the model also on some of the data sets are include examples which have these basically 2 compounds were like put together or in solution together when they went through the assay. So it captures those, yeah, as well.
Awesome. Second question.
Yeah, I had 2. One is kind of following on from the question asked earlier. So how does it deal with macromolecules or molecules that might have, not necessarily a polymer, but an oligomer with a significant 3D structure that would, present or hide functional groups?
Yeah, that's a great question. So there's the way that we represent the molecules in the ML model is as a graph. So it doesn't take into account any conformational information. So it's not, we don't need three-dimensional coordinates or anything of the atoms. And we find that this is basically improves, like strictly improves the performance, the predictive performance of the model. Because yeah, you can add a lot of noise if you get the wrong conformation.
And my second question, if I may, is if information is updated about a particular compound or a pair of compounds with respect to, crystallinity in certain solvents or pH behavior, how does the model update itself to take into account that new information?
You're saying like if there was a new study that came out?
Yeah, exactly.
Yeah, so one of the benefits of this model is that unlike, if you go to GPT or something, that's fixed. So if there's new information, it wouldn't necessarily have access to that. But this model that is analyzing these results right now is actively searching the internet for the latest research, the latest papers, et cetera, and it will, bring those in and summarize it. So not saying that, if you publish it yesterday, that it's going to be available, but it's much more up to date than just using a standard language model.
Thanks.
All right, well, we are out of time, and I apologize for skipping over the demo. I think we all saw on screen that BPA is bad.
Yeah, BPA is bad.
BPA is bad. I don't know what molecule this is, but
yeah.
I think we have to call it, guys.
Sounds good.
Really appreciate it and excellent work to all of the startups. And now I guess I'll pass back to Rui. We'll say a few words before we brainstorm, build, and bond.
Yes, I was told to be very quick, so I will be. The only thing I'll say is I hope is John still here? I hope John will agree that we're starting to chip away at that 80% of things that needs to be invented, right? There's a lot of potential there. So thank you, Alec, for moderating the second half. Thank you to all of our startups, large and small, for being part of this event. And at this point, I'm going to turn over to my colleague, Ashley Vestland, who will take you through the next set of proceedings. Thank you, everyone.
Thank you. And it's so nice to see all of you and great presentations today. So been really good. So we have some fun things coming up. Not that the other things weren't fun, but other fun things coming up now. So we have the speed networking session coming up at 5. Some of you have signed up for that, and I hope you know who you are. And if you have signed up, if you can just reverse your badges, you will find the magic star there with a color. And please be back in this room at 5, and you will find the right table for your group with something like that with the right star. But anyway, we'll sort you all out if you're a bit confused. If you can please empty this room because the networking is going to happen here and we need to prep the room. So if you can just take your belongings, that would be great. And for those who are not doing that, I believe there are some more tours. Although judging by the rain, I don't know how that's going to work out. Nathan, are you here? He's outside? Okay. Okay. If anyone wants to walk in the rain and see more of the campus, then please go out this way. And everyone else, the reception will be here at 6. But please go outside. But if you're in the speed networking, please be back and seated by 5. Thank you. See you then.